Hello there, and welcome to Science for Sleep, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we're heading towards something so extreme that it almost sounds made up. Not the biggest star ever discovered, not the brightest, not even the most massive. Instead, we're spending some time with one of the hottest stars known to exist, a stellar object called WR102. Now, heat is one of those things we think we understand quite well. We know what it feels like to step outside on a summer afternoon and immediately regret wearing a dark shirt. We know the sting of touching a mug of tea before it's cooled down. We know that ovens are hot, campfires are hotter, and that one seatbelt buckle left in direct sunlight somehow becomes hotter than the surface of common sense. But the universe has a habit of taking familiar ideas and stretching them far beyond anything our everyday experience prepares us for. WR102 is one of those examples. This is a star so hot that if you tried to compare it to the Sun using ordinary language, the comparison almost stops being useful. It's a bit like comparing a candle to a lightning strike, or a garden pond to an entire ocean. The numbers become so large that they begin to slip through our imagination. And yet, despite its extraordinary nature, WR102 is still a star. It's made from the same basic ingredients as countless other stars scattered across the cosmos. It was born, it changed, it evolved, and one day it will die. The difference is that it is living its life at an intensity few objects in the universe can match. Before we get there though, I'd love to ask you something. Where in the world are you listening from tonight? Are you stretched out in bed with the lights already off? Perhaps you're curled up on a sofa after a long day. Maybe you're listening through headphones while rain taps gently against a window. Or perhaps it's early morning where you are and the day hasn't quite started yet. And while you're thinking about that, here's another fitting question. How warm is the room around you right now? Comfortably cool? A little chilly? Maybe wrapped in blankets because your feet seem to operate under completely different climate rules than the rest of your body? Whatever the answer happens to be, it's safe to say that your surroundings are nowhere near the temperature of WR102. Not even remotely close. If you find these sleepy journeys through science relaxing, interesting, or simply a pleasant way to unwind before sleep, I'd be very grateful if you gave the video a like and perhaps subscribed as well. It helps this little corner of calm reach other curious people who might enjoy drifting off while learning something new about the universe. Now then, settle in, get comfortable, allow your shoulders to relax, let the day slowly drift into the background. Because tonight we're going to spend some time with a star that pushes heat to astonishing extremes. To begin understanding WR102, we need to talk about something surprisingly difficult. Not stellar physics, not nuclear fusion, not giant explosions. Heat. Simple heat. Or at least what we usually mean when we say something is hot. Most of us spend our entire lives dealing with temperature without ever thinking much about what it actually is. We know when something feels warm. We know when something feels cold. We know that ice belongs in drinks and that placing your hand on a hot stove is generally considered a poor life choice. But beneath those everyday experiences lies something fascinating. Temperature is really a measure of motion. More specifically, it measures how energetically particles are moving. The atoms and molecules inside everything around you are constantly jiggling, vibrating, bouncing, and colliding. Even objects that seem completely still are actually full of microscopic activity. A wooden table isn't truly motionless. A blanket isn't motionless. The air around you isn't motionless. At the atomic level, everything is busy. When particles move faster, temperature rises. When particles move more slowly, temperature falls. That's a simplification, of course, but it's a useful one. In many ways, heat is simply motion viewed from a very particular angle. Think about boiling water. As heat enters the water, its molecules begin moving more energetically. They collide more often. They move faster. Eventually, they move so vigorously that some escape entirely as steam. The water appears calm enough from a distance, but at the molecular level it's becoming increasingly chaotic. Now imagine continuing that process. Keep adding energy, keep increasing motion, keep raising the temperature. At some point, ordinary materials stop behaving in ordinary ways. Solids melt, liquids evaporate. Atoms lose electrons, matter itself begins changing state, and that is where stars enter the story. Stars are not simply hot rocks floating through space, they are enormous spheres of plasma. Plasma is often called the fourth state of matter. In plasma, atoms have been heated so intensely that electrons are stripped away from their nuclei. Instead of neutral atoms, you get a soup of charged particles. This state of matter dominates the visible universe. Lightning is plasma, the sun is plasma, many nebulae are plasma, and WR102 is plasma taken to extraordinary levels. But before we focus on that particular star, let's spend a moment with our own. The sun is already difficult to comprehend. The surface of the sun sits at roughly 5,500 degrees Celsius. That temperature is enough to vaporize nearly anything we encounter in everyday life. Still melts long before reaching it. Concrete fails long before reaching it. Most familiar materials simply stop being materials in any recognizable sense, and yet the sun's surface is actually considered relatively cool compared with some of the most extreme stars known. That's the part that surprises people. We tend to think of the sun as unimaginably hot because, from a human perspective, it absolutely is. But astronomy has a way of making impressive things seem modest. Imagine visiting a town where everyone is 7 feet tall. You might still be considered tall by ordinary standards, but suddenly your perspective changes. The sun experiences something similar when compared with stars like WR102. Astronomers classify stars into different categories based on characteristics such as temperature, colour, mass, and composition. Many of the stars visible in the night sky belong to familiar groups that have been studied for decades. Some are cooler and redder, some are hotter and bluer, some are small and long-lived. Others burn through their fuel quickly and dramatically. WR102 belongs to a category known as Wolf-Rayet stars. Even among astronomers, those words tend to attract attention. Wolf-Rayet stars are not ordinary stars. They represent a brief and extreme phase in stellar evolution. These objects are powerful, unstable, and astonishingly energetic. They are stars that have already lived remarkable lives and have reached a stage where they are shedding vast amounts of material into space. Imagine a star so intense that its own outer layers are being blasted away by the energy generated within. That gives you a rough idea of what we're dealing with. In fact, Wolf-Rayet stars lose mass at rates that would seem absurd if applied to our Sun. They generate fierce stellar winds that race outward at tremendous speeds. Every second, enormous quantities of matter are thrown into surrounding space. It's a bit like watching a candle burn down, except the candle weighs many times more than our Sun and is ejecting material across distances measured in billions of kilometers. The reason for this violence lies deep inside the star. Stars exist because gravity and pressure are locked in a constant struggle. Gravity tries to pull material inward. Fusion pushes outward. As long as those forces remain balanced, a star survives. But balance doesn't mean peace. Inside every star, unimaginable processes are taking place continuously. Hydrogen fuses into helium. Energy is released. Radiation pushes outward, gravity responds, the struggle continues. For most stars, including the Sun, this balance can last for billions of years. WR102 is not most stars. Its life is moving much faster. Massive stars consume their fuel at astonishing rates. This surprises many people. A larger fuel tank might seem like it should last longer. But stellar physics has different plans. Massive stars burn fuel far more aggressively. They are less like economical family cars and more like vehicles driving at maximum speed with the accelerator permanently pressed to the floor. As a result, the biggest and hottest stars often live the shortest lives. Some survive only a few million years, That may sound like a long time until you remember that our sun is over 4.5 billion years old. In stellar terms, WR102 belongs to the fast-living crowd, the cosmic equivalent of someone who somehow manages to compress an entire lifetime of activity into a remarkably short span. What's especially interesting is that stars like WR102 reveal what happens when nature pushes physical limits. Scientists often learn the most by studying extremes: the hottest deserts, the deepest oceans, the strongest storms, the most powerful earthquakes. Extreme cases expose details that ordinary situations tend to hide. Stars work the same way. When astronomers observe WR102, they aren't merely looking at a distant point of light. They're observing physics operating under conditions impossible to reproduce on Earth. They're seeing matter subjected to incredible temperatures. They're seeing stellar evolution approaching its final stages. They're seeing clues about how heavy elements spread through galaxies. And perhaps most importantly, they're seeing part of a process that ultimately connects to us. That might sound surprising. After all, WR102 exists far away from our daily lives. It doesn't affect our weather. It doesn't appear prominently in the night sky. Most people have never heard its name. Yet stars like this play an important role in the larger story of the universe. Every atom heavier than hydrogen and helium has a history. The carbon in your body, the oxygen you breathe, the calcium in your bones, the iron in your blood. All of those elements originated in stars. Some were forged during ordinary stellar lifetimes, others required violent stellar deaths. The universe wasn't born containing all the ingredients necessary for planets and life. Stars had to manufacture many of them first. In a sense, every star contributes to a long cosmic recycling program. Material forms stars. Stars create new elements. Those elements return to space. New stars and planets form. The cycle continues. WR102 happens to be participating in one of the most dramatic stages of that cycle, and the temperatures involved are difficult to overstate. The numbers are so extreme that they can lose meaning if presented too quickly. That's one reason we'll take our time with them. Because understanding truly enormous scales requires patience. Our brains evolved to judge distances across fields, temperatures around campfires, and time spans measured in days or years. They did not evolve to comfortably visualize conditions inside giant stars. Fortunately, we don't need to understand everything all at once. We can approach the subject gradually, piece by piece, question by question. And as we do, WR102 starts becoming something more than a collection of statistics. It becomes a place, a real object, a genuine star living out its final stages somewhere in the vastness of our galaxy. Heat is one of those things that feels completely familiar until somebody asks you to explain it. Most of us spend our lives interacting with temperature every single day. We check weather forecasts, we adjust thermostats, we wait for coffee to cool down, we complain when it's too hot in summer and too cold in winter. Heat feels like one of the most ordinary parts of existence. And yet, if someone suddenly asked, "What exactly is heat?" many of us would probably pause for a moment. We know what heat feels like. Understanding what it actually is turns out to be a little more interesting. To begin, let's imagine a perfectly ordinary mug of tea. Perhaps that's an easy thing to picture right now. A warm mug resting on a bedside table, a little steam rising from the surface. Nothing particularly dramatic. Now imagine shrinking yourself smaller and smaller until you're no longer looking at the mug as a whole. Instead, you're seeing the tiny particles that make up the water inside. At that scale, nothing is still. The water molecules are constantly moving. They bump into one another, they spin, they vibrate, they collide millions upon millions of times every second. The warmer the water becomes, the faster those particles move. The cooler it becomes, the slower they move. In many ways, temperature is simply a measurement of motion. Not motion that we can easily see, but motion happening at the microscopic level. This idea surprises people because heat often feels like a substance. Historically, many people believed that it actually was one. For centuries, scientists thought heat might be a special fluid called caloric. The theory suggested that warm objects contained more caloric and cold objects contained less. Heat appeared to flow from one object to another much like water moving between containers. At first glance, the idea seemed reasonable. After all, heat does move. Place an ice cube in warm water and energy flows from the warmer object to the colder one. Touch a metal spoon resting in a hot bowl of soup and the spoon becomes warm. Leave a cup of tea on a table and eventually it cools to match the surrounding room. Something is clearly moving. The question was what? Eventually scientists realized that heat wasn't a mysterious fluid at all. It was energy. More specifically, energy associated with the motion of particles. Once that understanding arrived, many strange observations suddenly made sense. Take friction, for example. Rub your hands together for a few seconds. You'll notice warmth almost immediately. You're not creating some magical heat substance. Instead, you're converting motion into thermal energy. The molecules in your skin begin moving more energetically. Temperature rises. The sensation of warmth appears. This same thing happens on much larger scales. A meteor entering Earth's atmosphere becomes incredibly hot because of interactions with air molecules. Mechanical systems generate heat through friction. Engines become warm while operating. Even tectonic activity deep within Earth creates heat through movement and pressure. Again and again, motion and temperature reveal themselves as close relatives. This relationship becomes even more fascinating when we start talking about extreme temperatures. Consider a winter day. Perhaps the temperature drops below freezing. Water turns into ice. Breath becomes visible. Puddles develop thin, glassy surfaces. To most people, that feels very cold, and it is. But from the perspective of physics, even ice contains enormous amounts of molecular motion. The particles haven't stopped moving. They've simply slowed down. To completely eliminate thermal motion, you would need to reach a temperature known as absolute zero. Absolute zero is one of the most important concepts in physics. It represents the lowest possible temperature. At this point, particles contain the minimum amount of thermal energy permitted by quantum mechanics. The temperature corresponds to minus 273.15 degrees Celsius. That's cold on a level that almost defies imagination. No natural location in the universe appears capable of reaching it perfectly. Scientists can come extraordinarily close in laboratories, but absolute zero itself remains just beyond reach. What's remarkable is that all temperatures we normally experience occupy a tiny portion of the possible range. A comfortable room might be 20 degrees Celsius. A hot summer day might reach 40. Boiling water sits at 100. An oven might operate around 200. These differences feel enormous to us because our bodies are sensitive instruments. A few degrees can determine whether we're comfortable or uncomfortable. A few dozen degrees can determine whether food cooks properly. But the universe is not limited by human preferences. Nature operates across scales that make our everyday temperatures seem almost insignificant. Let's return to the sun for a moment. The surface of our star reaches roughly 5,500 degrees Celsius. Already that number sounds astonishing. If you could somehow transport a piece of ordinary matter into those conditions, it wouldn't remain ordinary for very long. Chemical structures would fail, materials would vaporize, atoms would become increasingly energetic, and yet even the sun's surface is only part of the story. Move deeper toward its core and temperatures climb dramatically. Near the center, where nuclear fusion occurs, temperatures reach around 15 million degrees Celsius. At those conditions, matter behaves in ways completely unlike anything we encounter in daily life. Hydrogen nuclei move so energetically that they overcome their natural electrical repulsion and fuse together. This process releases tremendous amounts of energy. Every second, the sun converts hundreds of millions of tons of hydrogen into helium. It sounds almost unbelievable. Yet it has been doing exactly that for billions of years. Every sunrise you've ever seen has been powered by fusion reactions occurring deep within the solar core. Without them, Earth would be a frozen and lifeless place. Still, as impressive as the Sun appears, it is not the hottest star known, not even close. The universe contains stars operating at temperatures that make our local star seem relatively modest. That realization can be surprisingly difficult to absorb. After all, the Sun dominates our sky. It controls our climate. It powers ecosystems. It provides virtually all the energy supporting life on Earth. From a human perspective, it feels enormous and overwhelming. Astronomy, however, has a habit of introducing larger numbers, and then larger numbers after those. Eventually you encounter objects that seem almost unreasonable. WR102 belongs firmly in that category. Before we arrive there, though, it's worth exploring another question. What does hotter actually mean in a star? When we talk about a stove becoming hotter, we're generally describing a simple increase in temperature. Stars are more complicated. Temperature influences colour. It influences brightness. It influences radiation. It influences how atoms behave. And it even influences how a star evolves over time. One of the easiest ways to see this relationship involves looking at colour. Objects emit electromagnetic radiation depending on their temperature. Cooler objects tend to glow red. Hotter objects become orange, then yellow, then white, then blue. You can see a version of this in everyday life if you've ever watched metal being heated. As temperature rises, its colour changes. The same principle applies to stars. Red stars tend to be cooler. Blue stars tend to be hotter. Our sun appears yellow-white. Some stars glow deep orange, others shine brilliant blue. Astronomers can learn a tremendous amount simply by analysing starlight. The colour of a star provides clues about temperature. The spectrum of its light reveals information about chemical composition. Tiny details hidden within that light allow scientists to estimate mass, age, and evolutionary stage. In a sense, stars constantly tell us about themselves. The challenge is learning how to listen. Modern astronomy has become exceptionally good at doing exactly that. Using spectroscopy, scientists can break starlight into its component wavelengths, much like a prism creates a rainbow. Within those colours lie fingerprints left by different elements. Hydrogen leaves signatures. Helium leaves signatures. Carbon, oxygen, nitrogen, and many others leave signatures as well. By studying these patterns, astronomers can determine what a star contains and what physical processes are taking place inside it. This technique proved especially important when studying unusual stars. Objects like WR102 stand out because their spectra reveal extraordinary conditions. The light arriving from such stars carries evidence of tremendous temperatures and powerful stellar winds. Even from vast distances, astronomers can tell something unusual is happening. It's rather remarkable when you think about it. A star may be thousands of light years away. No spacecraft has visited it. No human will ever stand near it. And yet scientists can still estimate its properties using nothing more than the light reaching Earth. That's one reason astronomy often feels a little magical, despite being firmly grounded in physics. Information travels across enormous distances hidden within light itself, and with enough patience we can decode it. Another useful way to think about temperature involves energy density. Imagine two campfires. One is small and gentle. The other is enormous and roaring. Both are hot, but one contains much more energy. Stars operate according to similar principles. Temperature doesn't simply tell us something is hot. It tells us how much energy is concentrated within matter. Higher temperatures generally mean particles are moving more energetically. Collisions become more violent. Radiation becomes more intense. Physical processes accelerate. This matters tremendously for stars because fusion rates depend heavily on temperature. Raise the temperature inside a star and nuclear reactions occur more rapidly. More energy gets released, the star becomes brighter, fuel gets consumed faster, life expectancy decreases, This leads to one of astronomy's most interesting patterns. The biggest stars often live the shortest lives. At first glance, that seems backwards. A larger fuel supply should last longer, yet massive stars consume fuel at astonishing rates. It's the cosmic equivalent of a vehicle with a gigantic fuel tank, an absolutely terrible fuel economy. The engine is simply too powerful, the fuel disappears quickly. Stars like WR102 represent the extreme end of that trend. They burn with extraordinary intensity. The temperatures involved are so high that the star's outer layers become unstable. Powerful winds strip material away. Mass is lost continuously. The star effectively spends its life fighting against its own incredible energy output. That idea alone gives us a hint about just how unusual WR102 truly is. Most stars spend billions of years in relatively stable conditions. WR102 is living a much more dramatic existence. Its current state represents a brief phase in stellar evolution. A phase characterized by immense heat, tremendous energy, and ongoing transformation. Yet before we focus directly on that remarkable object, there is one final perspective worth considering. Human beings are strangely adapted to a very narrow thermal window. Our bodies operate within a tiny range of temperatures. A fever of just a few degrees can make us miserable. A larger change becomes dangerous. The temperatures supporting life on Earth occupy an incredibly small slice of the universe's possible thermal conditions. Beyond that narrow comfort zone lies a staggering range. The cold darkness between galaxies, the frozen surfaces of distant worlds, the blazing interiors of stars, the violent environment surrounding neutron stars and black holes. Nature is comfortable operating across extremes that would instantly destroy us, and perhaps that's one reason astronomy remains so captivating. It continually reminds us that our everyday experience represents only a small corner of reality. The universe is far larger, hotter, colder, stranger, and more energetic than intuition suggests. Not every star earns a reputation. Most stars spend their entire lives doing their work quietly. They form from clouds of gas, shine for millions or billions of years, and eventually fade into whatever fate their mass has prepared for them. Astronomers catalogue them, measure them, classify them, then move on to the next one among the hundreds of billions scattered throughout our galaxy. Every so often, though, a star appears that makes scientists stop and pay special attention. WR102 is one of those stars. Its name may not sound particularly memorable. In fact, it sounds more like a forgotten product serial number than one of the most extraordinary objects in the Milky Way. There are no dramatic words attached to it. No mythical references, no poetic nickname. Just 2 letters and 3 numbers, WR102, yet hidden behind that simple label is one of the hottest stars known to exist. Before we can understand why astronomers find it so fascinating, we should first answer a very basic question. What exactly is WR102? The first clue appears in those 2 letters. The WR stands for Wolf-Rayet. This places the star within a rare and unusual family known as Wolf-Rayet stars. The name comes from 2 French astronomers, Charles Wolf and Georges Rayet, who identified this peculiar class of stars in the 19th century. While studying stellar spectra in 1867, they noticed something strange. Most stars displayed familiar absorption lines. Wolf and Rayet found stars showing powerful emission features instead. The stars appeared to be broadcasting unusual signatures into space. At the time, nobody fully understood what they were looking at. Astronomy was still developing many of the tools needed to understand stellar physics. The discovery raised questions that would take decades to answer. Eventually, scientists realized these stars represented a particularly extreme stage of stellar evolution. Wolf-Rayet stars were not ordinary stars at all. They were stars undergoing tremendous internal and external changes, stars pushing themselves toward their limits, stars revealing what happens when nature turns the energy dial almost all the way up. WR102 belongs to that family, and even among Wolf-Rayet stars, it stands out. That alone should tell us something. Imagine joining a club composed entirely of Olympic athletes, then imagine becoming known as one of the most exceptional members of that already exceptional group. That's roughly what WR102 has accomplished in stellar terms. Astronomers estimate that WR102 lies thousands of light years away from Earth. The exact distance remains difficult to determine perfectly, but it resides within our own Milky Way galaxy. Far enough away that its light spends thousands of years travelling through space before reaching us. Think about that for a moment. The photons entering telescopes tonight began their journey long before many human civilizations existed in their current form. While kingdoms rose and fell, while languages evolved, while entire generations lived and disappeared, the light from WR102 continued crossing the galaxy. Only now is it arriving at Earth. Astronomy often works this way. Looking outward also means looking backward. The farther away an object is, the further into the past we see it. WR102 therefore appears not exactly as it is now, but as it was thousands of years ago. That idea can feel slightly strange at first. Imagine receiving a photograph that was taken centuries earlier and trying to determine what the subject looks like today. Astronomers perform a version of that task constantly. They observe ancient light and reconstruct present realities. Fortunately, the laws of physics remain remarkably reliable. By studying the light arriving from WR102, scientists can learn an enormous amount about the star itself, and the more they studied it, the more unusual it became. One reason WR102 attracts attention is its temperature. Current estimates place its surface temperature around 200,000 degrees Celsius. Some estimates vary slightly depending on methods and models, but the overall picture remains clear. This star is extraordinarily hot. To appreciate that number, it helps to compare it with something familiar. The Sun's surface temperature sits around 5,500 degrees Celsius. Already that figure feels immense. WR102 exceeds it by an astonishing margin. The difference is not merely noticeable, it is enormous. If the Sun represents a comfortable campfire by stellar standards, WR102 resembles a furnace operating at a completely different level. Of course, analogies eventually fail because human experience contains nothing remotely comparable. There is no everyday object capable of preparing us for temperatures like these. Even industrial processes reach their limits long before such conditions. Matter behaves differently, atoms behave differently, radiation behaves differently. The environment around the star becomes fundamentally hostile to anything resembling ordinary matter. But temperature alone does not tell the whole story. To truly meet WR102, we need to understand what kind of life it has lived. Every star begins with gravity. Somewhere within a giant cloud of gas and dust, material begins gathering together. Small concentrations become larger. Gravity strengthens. More material falls inward. Eventually the growing mass compresses enough for fusion to ignite. A star is born. The details depend heavily on mass. Small stars live slowly. Large stars live quickly. WR102 began life as a very massive star. Far more massive than our Sun, that initial mass determined everything that followed. Massive stars experience stronger gravity. Stronger gravity creates higher pressures. Higher pressures create higher temperatures. Higher temperatures accelerate fusion. Fusion releases more energy. The cycle feeds upon itself. As a result, massive stars shine brilliantly, but live comparatively short lives. Instead of stretching their fuel supply across billions of years, they burn through it at extraordinary rates. It's a little like comparing a candle to a blast furnace. Both consume fuel. One does so much more aggressively. WR102 belongs firmly in the blast furnace category. The star has already passed through several stages of stellar evolution. The hydrogen that once dominated its outer layers has largely disappeared. Powerful stellar winds have stripped away enormous amounts of material. As those layers vanished, deeper regions became exposed. Astronomers are effectively seeing parts of the star that would normally remain hidden beneath outer layers. This is one reason Wolf-Rayet stars are so valuable scientifically. They provide a glimpse into processes normally concealed inside massive stars. In a sense, WR102 is revealing its internal structure to the universe. It's doing so unintentionally, of course. Stars don't volunteer information, but physics leaves clues everywhere. The light escaping from WR102 carries evidence of what is happening beneath the surface. When astronomers analyse that light, they find signatures indicating a star undergoing remarkable changes. They see helium. They see heavier elements. They see evidence of intense mass loss. They see indications of extreme temperatures. Piece by piece, a picture emerges. And that picture is dramatic. One of the most striking characteristics of WR102 is the strength of its stellar wind. Stars continuously lose small amounts of material. The Sun does this as well. Solar wind flows outward from our star all the time. Earth experiences its effects through interactions with our planet's magnetic field. Auroras provide beautiful reminders of that process. WR102 takes the concept of stellar wind and amplifies it tremendously. Material streams away from the star at astonishing speeds. These outflows carry vast quantities of matter into surrounding space. The star is literally shedding itself. Imagine standing in a windstorm so powerful that pieces of a mountain were being stripped away and carried into the atmosphere. Even that image falls short of the reality. The scale involved is simply too large. Yet this mass loss plays a critical role in the star's evolution. Every particle carried away changes the future of WR102. Every gust of stellar wind alters what the star will eventually become. Astronomers believe that WR102 is approaching the final stages of its life. Not immediately, at least from a human perspective. Stars still operate on timescales far longer than human lifetimes, but compared with ordinary stars, WR102 is nearing the end of its journey. The fuel reserves that once powered its youthful stages have been transformed. The internal structure continues evolving. Future changes are inevitable. Eventually the star will exhaust its remaining options. When that happens, the outcome is expected to be spectacular. Massive stars do not leave quietly. They tend to announce their departure with tremendous violence. We'll explore that future later. For now, it is enough to recognise that WR102 exists in a temporary phase, a brief and extraordinary moment within the life of a very massive star. That temporary nature makes the object even more interesting. Astronomers are fortunate to observe it at all. The Wolf-Rayet phase represents only a small fraction of a massive star's total lifespan. Compared with longer stages of stellar evolution, it passes relatively quickly. Finding one of the hottest known examples during this brief period is a bit like arriving at exactly the right moment to witness a rare natural event. The timing matters. Without it, we might never have learned so much about these extreme objects. Another fascinating aspect of WR102 is how different it appears from our intuitive image of a star. Many people imagine stars as giant glowing spheres similar to the Sun, smooth, stable, predictable. WR102 challenges that image. This is not a calm object quietly illuminating surrounding space. It is an active and evolving system. Material is flowing outward. Radiation is pouring into space. Internal reactions continue reshaping its future. The star exists in a state of ongoing transformation. In many ways, it resembles a cosmic engine operating at tremendous power. The comparison isn't perfect, but it captures something important. WR102 is dynamic. It is not simply sitting there. Processes unfold continuously. Energy moves, matter moves. Change never stops. And perhaps that's one reason these stars capture scientific attention so effectively. They reveal the universe at its most energetic. Not the gentle universe of quiet nights beneath familiar constellations. The universe of extremes. The universe where temperatures reach astonishing levels. Where stellar winds race outward at immense speeds. Where stars burn through their lives with extraordinary intensity. Long before astronomers understood what WR102 truly was, they knew it belonged to a very unusual family. In astronomy, families matter. Not because stars gather together for holidays or argue about politics over dinner, but because classification helps scientists understand how objects form, evolve, and eventually disappear. When astronomers discover a strange object, one of the first questions they ask is simple. What kind of thing is this? Sometimes the answer is straightforward. A star might belong to a common category with millions of known examples. Other times the answer becomes much more interesting. WR102 belongs to a group so unusual that even among astronomers, the words Wolf-Rayet star immediately suggest something extreme. These are not ordinary stars. They are not stable middle-aged stars like our Sun. They are not gentle red dwarfs quietly burning hydrogen for trillions of years. They are not stars settling comfortably into long, predictable lives. Wolf-Rayet stars are survivors of a much more dramatic journey. To understand why they are so strange, it helps to begin with an important fact about stars. Most stars spend the majority of their existence trying very hard not to collapse. Gravity constantly pulls inward. Fusion constantly pushes outward. As long as those forces remain balanced, the star survives. This balance is surprisingly delicate. Too much gravity and the star contracts. Too much outward pressure and the star expands. For billions of years, many stars manage to maintain this equilibrium. The Sun has been doing it for roughly 4.5 billion years. It still has billions of years remaining before major changes arrive. Wolf-Rayet stars tell a very different story. They begin life enormously massive. Not slightly larger than the Sun, not 2 or 3 times larger, often dozens of times more massive. That initial mass changes everything. Massive stars are born with advantages and disadvantages. The advantage is obvious. More mass means more fuel. The disadvantage is less obvious. More mass also means stronger gravity. Stronger gravity compresses the stellar core more intensely. Higher pressure creates higher temperatures. Higher temperatures accelerate fusion. The star consumes fuel at extraordinary rates. Imagine 2 vehicles. One is a small economical car. The other is an enormous machine equipped with an engine so powerful it could probably tow a small building. Which vehicle burns fuel faster? The larger one, of course. The same principle applies to stars. Massive stars live fast. Very fast. A star with many times the Sun's mass might live only a few million years. That sounds like a long time until you compare it to the Sun's expected lifespan of roughly 10 billion years. Suddenly, a few million years starts looking surprisingly brief. Wolf-Rayet stars are the descendants of those massive stars. They represent a later stage of stellar evolution, a stage that most stars never reach because most stars simply aren't massive enough. This is one reason Wolf-Rayet stars are relatively rare. The universe produces far fewer giant stars than small ones, and the Wolf-Rayet phase itself lasts only a short period. Those 2 factors combine to create a genuinely uncommon population. Finding one is a bit like finding a professional athlete in a city full of ordinary people. Finding one as extreme as WR102 is even rarer. The story of Wolf-Rayet stars begins with observation. Back in the 19th century, astronomers relied heavily on spectroscopy. This technique involves studying the light produced by celestial objects. A star's light contains information hidden within it. Break that light into a spectrum and patterns begin to emerge. Different elements leave distinctive signatures. Hydrogen leaves one set of fingerprints, helium leaves another. Carbon, oxygen, nitrogen, and many others all reveal themselves through characteristic spectral lines. Most stars showed familiar patterns. Then Charles Wolfe and Georges Rayet encountered something unusual. The stars they observed displayed strong emission lines. This was unexpected. Instead of merely absorbing specific wavelengths, these stars seemed to be producing intense emissions from certain elements. The stars were announcing themselves in a different way. At first, nobody knew exactly what that meant. Astronomy was still developing. Stellar physics remained incomplete. Many mysteries remained unsolved. Over time, however, scientists pieced together the answer. The strange spectral signatures came from powerful stellar winds and unusual atmospheric conditions. These stars were shedding material into space at remarkable rates. What astronomers were seeing was evidence of violence. Not explosions, not collisions, but continuous stellar violence, material streaming away from the star, outer layers being stripped away, mass disappearing into surrounding space. The stars were literally eroding themselves. That realization transformed Wolfe-Rayet stars from curiosities into major scientific targets. Suddenly, astronomers had a way to study some of the most extreme stellar environments in existence. And the more they learned, the stranger these stars became. One defining characteristic of Wolfe-Rayet stars is their powerful stellar winds. We've mentioned stellar winds before, but it's worth slowing down and appreciating what that actually means. The Sun has a stellar wind. Particles constantly stream outward from our star. Earth exists inside this flow. Our magnetic field protects us from most of its effects. Auroras provide visible reminders that the solar wind is always present. The Sun's wind feels impressive until you compare it with Wolfe-Rayet stars. Then it starts looking relatively modest. A Wolfe-Rayet star can lose enormous amounts of material every year. These winds travel at astonishing speeds, thousands of kilometers per second in some cases. Imagine a hurricane. Now imagine a hurricane moving thousands of times faster. The comparison quickly breaks down because human weather simply cannot compete with stellar weather. The energy scales are entirely different. The winds surrounding Wolfe-Rayet stars are among the most powerful known, and they aren't occasional events. They operate continuously, hour after hour, day after day, year after year. The star constantly throws material into space. This creates another interesting consequence. As outer layers disappear, deeper layers become exposed. Think about peeling an onion. Remove enough outer layers and eventually you reach regions normally hidden from view. Wolfe-Rayet stars undergo something similar, except instead of revealing vegetable layers, they reveal the products of nuclear fusion. Material that would normally remain buried inside the star becomes visible. Astronomers can observe elements that originated deep within stellar interiors. That makes Wolfe-Rayet stars incredibly valuable scientifically. They allow researchers to study processes that are usually concealed. In a sense, these stars reveal their internal secrets earlier than expected. Most stars keep those secrets hidden until their deaths. Wolfe-Rayet stars begin exposing them while still alive. Not every Wolfe-Rayet star looks exactly the same, however. Astronomers divide them into several categories. Some are rich in nitrogen, others show strong carbon signatures, some reveal oxygen. These differences provide clues about evolutionary stages. They tell scientists which fusion processes dominate within the star. They reveal how much material has already been lost. They help reconstruct the object's history. It's a bit like examining tree rings. Except instead of studying wood, astronomers study light. The details hidden in spectra allow them to reconstruct stellar biographies. WR102 belongs to one of the most advanced groups. That fact alone tells astronomers something important. The star has already experienced tremendous change. It is not at the beginning of its story. It is much closer to the end. Massive stars evolve rapidly. Hydrogen fusion eventually gives way to helium fusion. Then heavier elements begin forming. Each stage becomes progressively shorter. The star races through evolutionary milestones. Conditions inside become increasingly extreme. The core changes. The outer layers respond. The future approaches quickly. Wolf-Rayet stars occupy a particularly dramatic period during that process. They represent stars that have already burned through enormous amounts of fuel, stars whose outer envelopes have largely disappeared, stars revealing deeper layers forged through intense nuclear reactions. It's almost as if nature temporarily pulls back a curtain. For a brief moment, astronomers gain access to processes normally hidden from observation. That brief moment is invaluable. Without Wolf-Rayet stars, our understanding of stellar evolution would be far less complete. Another reason these stars matter involves chemistry. Specifically, the chemistry of galaxies. Everything heavier than hydrogen and helium had to come from somewhere. The early universe contained mostly simple elements. Complex chemistry arrived later. Stars became factories producing heavier elements through fusion. Massive stars proved especially important. They generated many of the ingredients necessary for planets, oceans, atmospheres, and eventually life. Wolf-Rayet stars contribute to that process. Their winds scatter enriched material throughout surrounding space. Carbon, oxygen, nitrogen, other heavy elements. These materials mix with interstellar gas clouds. Future generations of stars inherit them. Future planets inherit them. Eventually, living organisms inherit them as well. This means Wolf-Rayet stars participate in one of the most important cycles in the cosmos, the recycling of matter. Atoms forged inside stars do not remain trapped forever. They travel, they spread, they become part of new systems. The carbon in your body may have originated inside a massive star billions of years ago. The oxygen you breathe may have a similarly ancient history. Stars live, stars die. Their material continues onward. Wolf-Rayet stars play a significant role in that ongoing story. Despite their importance, they remain difficult objects to study. Part of the challenge comes from rarity. There simply aren't many nearby examples. Another challenge comes from complexity. These stars are difficult to model. Their winds interact with radiation. Their internal structures evolve rapidly. Their atmospheres behave differently from those of ordinary stars. The physics becomes complicated. Fortunately, modern telescopes have dramatically improved our ability to investigate such objects. Ground-based observatories contribute valuable data. Space telescopes provide additional information. Computers allow scientists to build increasingly sophisticated models. Each improvement reveals new details. Each observation refines our understanding. And repeatedly, Wolf-Rayet stars prove even more fascinating than expected. One particularly striking aspect of these stars is how unstable they can appear compared to ordinary stars. The sun feels dependable, reliable, predictable. It rises every morning and behaves much as it did yesterday. Wolf-Rayet stars feel different. Not because they explode randomly every afternoon, but because they exist much closer to physical limits. Their energy output is immense. Their winds are immense. Their mass loss rates are immense. Everything about them operates near extremes. That makes them dynamic objects. Living laboratories for astrophysics. Places where theories can be tested against reality. WR102 represents one of the most remarkable examples of that category. Its temperature places it among the hottest known stars. Its evolutionary state places it near the end of a massive stellar life. Its winds reveal ongoing mass loss. Its light carries evidence of extraordinary physical conditions. If Wolf-Rayet stars are already unusual, WR102 sits near the far edge of that unusual group. And perhaps the most fascinating part is this. The very characteristics that make Wolf-Rayet stars spectacular are also signs of their mortality. The powerful winds, the exposed fusion products, the immense temperatures. The rapid evolution. None of these indicate stability. They indicate change. These stars are approaching their final act. The processes making them scientifically valuable are the same processes preparing them for eventual destruction. Massive stars live intensely. Wolf-Rayet stars live even more intensely. WR102 may represent one of the most extreme examples known, which naturally leads to the next question. If Wolf-Rayet stars are already among the most extraordinary stars in the universe, what specific conditions allow WR102 to reach such astonishing temperatures in the first place? And why does this particular star burn so much hotter than almost anything else astronomers have ever observed? At first glance, WR102 seems almost impossible. When people hear that it is one of the hottest stars ever discovered, the natural reaction is usually the same. How? What could possibly make a star reach such extraordinary temperatures? After all, stars are already hot by definition. The Sun's surface sits at roughly 5,500 degrees Celsius. That alone is enough to vaporize almost anything we encounter in everyday life. Many blue stars are significantly hotter. Some massive stars exceed 30,000 or even 40,000 degrees Celsius at their surfaces. Those numbers already stretch the imagination. Then along comes WR102, a star with a surface temperature estimated around 200,000 degrees Celsius. Suddenly, even the hottest ordinary stars begin to look modest. The answer to this mystery begins with something unexpected. WR102 is not extraordinarily hot because it gained something. It is extraordinarily hot because it lost something. More specifically, it lost a great deal of itself. To understand why that matters, imagine a campfire. When you stand several feet away, you feel warmth. Move closer and the heat becomes stronger. Move even closer, and eventually it becomes uncomfortable. The fire itself has not changed. Your position relative to the hottest region has changed. Something similar happened to WR102 during its evolution. For most of its life, the hottest regions of the star remained buried beneath thick outer layers. Those layers acted almost like insulation, not in the sense of trapping heat entirely, but in the sense that they concealed the deeper, more extreme parts of the star from outside observers. Then the star began stripping those layers away, slowly at first, then more aggressively. Eventually, enormous portions of its outer envelope disappeared. The result was extraordinary. The deeper and hotter regions became exposed. Astronomers were no longer observing the cooler outer atmosphere that once surrounded the star. They were seeing much closer to the incredibly energetic layers underneath. In a sense, WR102 became a star with its protective covering removed. To appreciate how dramatic this process was, let's go back to the beginning. Millions of years ago, WR102 likely looked very different. It began life as an extremely massive star, far larger than the Sun, far brighter, far more powerful. Its immense mass created enormous gravitational pressure inside the core. That pressure compressed matter to extraordinary densities. Temperatures rose, fusion accelerated, energy production became enormous. From the moment it formed, WR102 lived a much more intense life than our Sun ever would. The Sun is remarkably patient. It burns fuel steadily, carefully, efficiently. Its expected lifespan measures roughly 10 billion years. WR102 never had that luxury. Massive stars consume fuel with astonishing speed. The larger the star becomes, the more aggressively it burns. This often surprises people. A star containing more fuel seems like it should live longer. Instead, the opposite happens. The star's gigantic mass creates such extreme conditions that fuel consumption skyrockets. Imagine two candles. One burns quietly, the other burns like a flamethrower. Which survives longer? The answer is obvious. WR102 spent millions of years operating more like the flamethrower. As fusion accelerated, radiation pressure increased. Energy poured outward from the core. The star became increasingly luminous. At the same time, something else was happening. The radiation escaping from the star began pushing against the outer layers. This process gradually intensified. The result was the development of powerful stellar winds. Now, we've discussed stellar winds before, but it is worth slowing down because they are central to WR102's story. When most people hear the word wind, they think of weather, a gentle breeze, a storm, air moving across Earth's surface. Stellar winds are entirely different. They consist of charged particles and material flowing away from a star. The sun produces a stellar wind continuously. Earth exists inside it. Without our magnetic field, life would face serious challenges. Yet compared with WR102, the sun's wind is relatively mild. The winds surrounding WR102 are astonishing. Material streams outward at thousands of kilometers per second. Every second, the star loses enormous quantities of matter. Imagine carrying a bucket of water to a sink and pouring it out. Now imagine doing that continuously for years. Then imagine replacing the bucket with a mountain. Even that comparison falls short. The amount of mass involved is difficult to comprehend. For millions of years, WR102 has been shedding itself. The star has effectively been peeling away layer after layer. What makes this especially important is where those layers came from. The outer atmosphere represented some of the cooler regions of the star. Not cool by human standards, of course. Still extraordinarily hot, but cooler relative to the deeper layers. As stellar winds removed material, deeper regions gradually emerged. The process resembles erosion. Imagine a mountain exposed to wind and rain for millions of years. Eventually deeper rock becomes visible. Features hidden beneath the surface emerge. Wolf-Rayet stars experience a cosmic version of that process, only instead of exposing stone, they expose increasingly energetic stellar layers. This is one reason Wolf-Rayet stars fascinate astronomers. They provide access to regions normally hidden from view. Ordinary stars keep many secrets buried beneath thick envelopes of gas. WR102 has lost much of that envelope. The result is like opening a machine and suddenly seeing components that are usually concealed behind protective panels. And what astronomers saw was extraordinary. The exposed layers revealed temperatures vastly higher than expected in ordinary stars. Fusion products became visible. The star's spectrum changed dramatically. Evidence accumulated that WR102 had entered an exceptionally advanced evolutionary stage. By this point, the star was no longer behaving like a typical massive star. It had become something rarer, something more extreme. A Wolf-Rayet star nearing the final stages of its life. The loss of outer layers also altered the star's appearance in another important way. To understand this, think about the sun. When we look at the sun, we are not seeing its core. The core is buried beneath hundreds of thousands of kilometers of material. The light eventually reaching us originates from outer layers. Those layers determine much of what we perceive. If the sun somehow lost vast portions of its outer structure, we would observe something very different. Much hotter regions would become visible. Surface temperature estimates would rise dramatically. The star would appear transformed. That is essentially what happened to WR102. Its current temperature reflects layers that normally remain hidden in less evolved stars. We are observing regions much closer to the star's powerful interior. The effect is dramatic. Instead of tens of thousands of degrees, temperatures climb toward 200,000 degrees Celsius. Numbers like that quickly become difficult to visualize. Our brains simply aren't designed for them. Human beings evolved to judge temperatures involving fire, sunlight and weather, not temperatures capable of stripping atoms apart. Yet that is exactly the environment surrounding WR102. At such temperatures, matter behaves differently. Atoms lose electrons, plasma dominates, radiation becomes intense. The star floods surrounding space with enormous quantities of ultraviolet energy. Everything about the environment becomes more energetic. The chemistry changes, the physics changes, the entire character of the star changes. Another fascinating consequence involves colour. Many people assume hotter stars simply become brighter versions of familiar stars. Reality is more complicated. As temperatures rise, more energy shifts into ultraviolet wavelengths. Eventually, much of the star's output moves beyond what human eyes can detect. Ironically, an incredibly hot star can become less visually impressive than expected, because so much of its energy exists outside visible light. If human eyes could naturally see ultraviolet radiation, the universe would look very different. Objects like WR-102 would appear far more dramatic. Fortunately, telescopes allow astronomers to detect wavelengths invisible to us. Using specialized instruments, scientists can study the tremendous energy escaping from stars like WR-102. The observations reveal a stellar environment operating at astonishing extremes. Yet perhaps the most remarkable part of this story is that the process remains ongoing. WR-102 is not finished losing mass. The winds continue. Material continues streaming into space. The star continues evolving. Its story is still unfolding. Every year that passes brings subtle changes. Every year removes a little more material. Every year moves the star closer to its eventual fate. And that fate is linked directly to the processes making it so hot today. The loss of outer layers is not merely a side effect, it is part of the final act. The star is exposing increasingly advanced fusion products. It is revealing deeper stages of nuclear burning. Inside the core, heavier elements continue forming. Conditions become more extreme. The future becomes increasingly unavoidable. Astronomers often describe massive stars as living fast and dying young. WR-102 may be one of the best examples of that principle. Its incredible temperature is not a sign of youthful vitality. Quite the opposite. It is evidence of maturity, evidence of a star approaching the end of a remarkable journey. That idea can feel counterintuitive. We often associate heat with growth and strength. In stellar evolution, however, extreme temperatures can signal approaching collapse. The star burns hotter because its life has progressed further. The exposed layers reveal processes that occur near the end. In a sense, WR-102's astonishing temperature is a glimpse of mortality. The star has shed enough of itself to reveal the powerful engine underneath, and that engine is running at extraordinary intensity. The comparison that comes to mind is an old machine operating at maximum output, panels removed, internal components exposed, every system working furiously, everything visible, everything active, nothing hidden. That visibility is precisely what makes WR-102 so valuable scientifically. Astronomers rarely get opportunities to study stars at such an advanced stage. Most stars spend the majority of their existence in comparatively stable conditions. Rayet stars provide a brief window into something more dramatic. They reveal what happens when stellar evolution accelerates toward its conclusion. They show how massive stars transform. They show how elements are distributed throughout galaxies. They show how future supernovae prepare themselves long before the explosion occurs. UR-102 happens to be one of the most extreme examples currently known, and despite everything we've discussed so far, there remains an important question. We've talked about temperatures, we've talked about stellar winds, we've talked about lost outer layers, but numbers alone never fully capture reality. What would these conditions actually feel like? How hostile is the environment surrounding a star like WR-102? If it were somehow possible to travel toward it, what would happen as you approached one of the hottest stars in the universe? Imagine for a moment that the greatest challenge facing you today is not a busy schedule, an overflowing inbox, or trying to remember where you left your keys. Instead, imagine you're preparing for a journey, not across an ocean, not across our solar system, but toward one of the hottest stars ever discovered, WR-102. Now, before we begin, it's worth mentioning that this is very much an imaginary trip. In reality, no spacecraft humanity has ever built could survive such an expedition. No material we currently possess could comfortably handle the environment waiting near this star. Even the idea of approaching it pushes engineering into the realm of fantasy. Still, thought experiments are useful. Astronomers use them all the time. Sometimes the easiest way to understand something enormous is to imagine experiencing it directly. So let's begin far away. very far away. At a comfortable distance, WR102 would appear much like many other stars, a brilliant point of light suspended against darkness. From thousands of light years away, it doesn't look especially threatening. Stars rarely do. That's one of the interesting things about astronomy. Distance hides violence. A supernova can briefly outshine entire galaxies, yet from Earth, it may appear as nothing more than an unusually bright point in the sky. Black holes reshape entire regions of space, yet remain invisible to human eyes. The universe often disguises its most dramatic objects behind vast distances. WR102 is no exception. From Earth, it looks harmless. Approach it, however, and the illusion quickly disappears. Let's imagine a magical spacecraft capable of ignoring practical limitations, a ship that can travel wherever curiosity leads. As we move closer, the first thing we would notice is brightness, not warmth, not temperature, brightness. The star pours enormous amounts of energy into space. Long before heat becomes a concern, radiation becomes impossible to ignore. The star dominates the sky. Its light overwhelms surrounding darkness. Every surface inside the spacecraft becomes illuminated. The familiar concept of night begins disappearing. The closer we travel, the more overwhelming the star becomes. This happens because stars don't merely produce visible light. They emit energy across a vast range of wavelengths. Visible light represents only a tiny fraction of the electromagnetic spectrum. WR102 produces enormous amounts of ultraviolet radiation, far more than our Sun. In fact, much of the star's energy output exists beyond what human eyes can naturally detect. If our vision evolved differently, the star would appear even more astonishing. We would see an environment flooded with ultraviolet energy. The entire region surrounding WR102 would seem alive with invisible brilliance. At this stage of our imaginary journey, another problem begins emerging: radiation. The word itself often sounds mysterious. In reality, radiation simply means energy travelling through space. Sunlight is radiation. Radio waves are radiation. Heat radiating from a fireplace is radiation. The difference lies in energy levels. Near WR102, those energy levels become extreme. The star releases powerful ultraviolet photons capable of stripping electrons from atoms. This process is called ionization. It transforms ordinary atoms into charged particles. The environment surrounding the star becomes filled with highly energetic plasma. Space itself starts behaving differently. The gas around WR102 isn't calm, it isn't empty, it isn't peaceful. Instead, it exists in a state of continuous excitation. Matter absorbs energy. Electrons break free, particles collide. Radiation flows endlessly outward. Even from great distances, the star begins influencing its surroundings. Continue moving closer. The star grows larger, brighter, more intimidating. At some point, our comfortable comparisons begin failing. We can compare mountains to larger mountains, cities to larger cities, oceans to larger oceans. Temperature becomes harder. There is simply nothing in ordinary human experience that resembled 200,000 degrees Celsius. Nothing. Not volcanic lava. Not industrial furnaces. Not nuclear reactors. Nothing. The numbers become so extreme that intuition stops helping. Instead, we must think in terms of consequences. What does that temperature actually do? The answer is straightforward. It destroys normal matter. At such temperatures, atoms struggle to remain intact. Electrons are stripped away. Molecules cannot survive. Chemical structures collapse. The distinction between familiar materials begins disappearing. Everything becomes plasma. Everything becomes charged particles. Everything becomes energy and motion. Imagine taking a block of ice, then heating it. Eventually it becomes water. Heat it further and it becomes steam. Keep going and the molecules themselves break apart. Continue further and atoms lose electrons. push temperature high enough, and ordinary matter no longer resembles anything we recognise. WR102 exists in precisely that realm. The environment near the star is not merely hot, it is so energetic that matter itself behaves differently. As our spacecraft approaches further, we encounter another remarkable feature, the stellar wind. Earlier we discussed how Wolf-Rayet stars lose material. Now we can appreciate what that actually means. Imagine standing outside during a windy day. Leaves move, branches sway, perhaps your hair gets blown around. Now increase the wind speed. Imagine a hurricane. Trees bend, structures strain, debris flies through the air. The atmosphere becomes dangerous. Now multiply that scale beyond anything Earth can produce. The stellar wind flowing away from WR102 travels thousands of kilometers every second, not every hour, not every minute, every second. These are speeds difficult to visualize. A passenger jet might travel around 900 kilometers per hour. WR102's wind moves thousands of kilometers per second. The difference is staggering. Material blasted away from the star races outward at tremendous velocity. Our imaginary spacecraft would encounter an environment filled with fast-moving charged particles. It would be less like sailing through calm space and more like attempting to travel through a continuous particle storm. Everything near WR102 is moving. Everything is energetic. Everything is extreme. The star doesn't simply sit there glowing. It actively reshapes its surroundings. This is one reason Wolf-Rayet stars are considered such important cosmic engines. They don't merely illuminate space, they transform it. They inject energy. They inject matter. They inject newly created elements. Their influence extends far beyond their visible surfaces. Now let's move even closer. At this distance, the star dominates everything. There is no meaningful sky anymore, only WR102. The star occupies an enormous portion of our view. Its brightness becomes overwhelming. Its radiation becomes deadly. Its wind becomes relentless. And something fascinating happens to our perception. The closer we get, the less the star resembles a simple object. From Earth, stars often appear serene, almost peaceful. Tiny points of light scattered across darkness. Close up, that illusion disappears completely. Stars are not peaceful. Stars are ongoing nuclear events. The sun only feels calm because it sits approximately 150 million kilometers away. Distance softens reality. Remove that distance and stars reveal their true nature. WR102 reveals it dramatically. Deep inside the star, fusion reactions continue generating immense amounts of energy. Those reactions drive everything we observe: the radiation, the temperature, the stellar wind, the mass loss, the brightness. Everything originates from processes occurring far beneath the visible layers, and those processes are astonishing. Atoms are colliding under extraordinary pressure. Nuclei are merging. Energy is being released according to Einstein's famous equation. Tiny amounts of mass transform into tremendous amounts of energy, second after second, year after year. The star continues operating. It never pauses. It never rests. It simply burns. This raises an interesting question. Would we actually feel heat near WR102? The answer is yes, although perhaps not in the way people imagine. Heat transfer in space works differently than heat transfer on Earth. There is no atmosphere carrying warmth through convection, no air touching your skin. Instead, energy arrives primarily through radiation. The sun warms Earth this way. The energy travels across space and eventually reaches our planet. WR102 does the same thing, only far more intensely. The closer you move, the more radiation you receive. Eventually the energy becomes overwhelming. Surfaces heat rapidly. Materials fail. Electronics break down. Protective systems collapse. Even hypothetical future technologies would struggle. The star's environment is simply too extreme. In fact, One of the most interesting things about WR102 is that its temperature alone does not tell the whole story. Temperature measures how energetic particles are. Brightness measures how much energy is being emitted. The two are related but not identical. A small object can be extremely hot. A larger object can emit more total energy. Astronomers therefore examine multiple properties simultaneously: temperature, luminosity, mass, composition, wind speed, all contribute to the overall picture, and that picture reveals one of the most extraordinary stars known. At some point during our journey, another realization would emerge. WR102 is not meant to last. That sounds dramatic, but it's simply stellar evolution. Stars like this burn through their lives rapidly. The very qualities making WR102 fascinating are signs that its future is limited. The tremendous temperatures indicate advanced evolution. The powerful winds indicate significant mass loss. The exposed layers indicate a star nearing its final stages. In other words, everything we admire about WR102 also hints at its eventual fate. Imagine an athlete sprinting at maximum speed. The performance is impressive, but it cannot continue forever. The same principle applies here. WR102 burns with extraordinary intensity. The universe allows such brilliance. The price is longevity. Every second the star consumes fuel. Every second material escapes. Every second it moves closer to its conclusion. And yet there is something strangely beautiful about that reality. Not because destruction is beautiful, but because it reveals how dynamic the universe truly is. Stars are not permanent fixtures. They are processes. They change. They evolve. They live finite lives. WR102 simply experiences those changes more dramatically than most. By now, our imaginary spacecraft has reached a distance where survival becomes impossible. The environment is too hostile, the radiation too intense, the temperatures too extreme. No human observer could continue. No ordinary matter could comfortably endure. The stellar furnace wins. And perhaps that is the most useful lesson from this thought experiment. Numbers alone can become abstract. 200,000 degrees Celsius is an impressive statistic. Imagining what that actually means creates a deeper understanding. WR102 is not merely a hot star. It is an environment where familiar physics gives way to more extreme behavior. A place where atoms lose electrons. A place where stellar winds race outward at astonishing speeds. A place where energy pours into space with incredible intensity. A place where a massive star is revealing deeper layers of itself while racing toward its future. The closer we look, the less WR102 resembles an ordinary star and the more it resembles a gigantic natural engine operating near the limits allowed by physics. And while the temperatures themselves are remarkable, they're only part of the story. Because all that escaping material, all those powerful winds and all that energy flooding into surrounding space raise another fascinating question. If WR102 is constantly throwing pieces of itself away, just how powerful are those stellar winds, and what happens when one of the fiercest outflows in the universe begins reshaping everything around it? Most stars spend their lives holding themselves together. Gravity pulls inward, fusion pushes outward, a balance emerges, the star survives. From a distance, this arrangement can look surprisingly calm. Even our sun appears peaceful when viewed from Earth. It rises, it sets, it illuminates the sky. Most days it feels dependable and predictable, yet the reality is more complicated. The sun constantly loses material. Particles stream away from its surface every second. This outflow, known as the solar wind, extends far beyond the planets. Earth moves through it continuously. The entire solar system exists inside a giant bubble carved into interstellar space by the sun's influence. That fact alone is remarkable, and yet, compared to WR102, the sun's wind is almost gentle. If the solar wind is a steady river, The winds surrounding WR102 are more like a cosmic hurricane operating without interruption for hundreds of thousands of years. In fact, one of the defining features of Wolf-Rayet stars is not simply their temperature, it is their astonishing ability to throw themselves into space. WR102 is losing mass right now. Not occasionally, not during rare eruptions, continuously. Every second, material leaves the star and races outward into the surrounding darkness. The scale of this process is difficult to appreciate because human experience offers few useful comparisons. When a tree loses leaves, it remains fundamentally the same tree. When a mountain loses a few rocks, it remains fundamentally the same mountain. When a river loses water, fresh water quickly replaces it. WR102 is different. The material leaving the star is part of the star itself. Every gust of stellar wind removes matter that once belonged to the star's outer layers. It is as though the star is slowly evaporating into the galaxy. The process is gradual from a human perspective. Nobody would notice changes by watching for an afternoon, but across thousands and millions of years, the effect becomes enormous. Entire portions of the star disappear. Astronomers often describe Wolf-Rayet stars as stripped stars. That description is surprisingly accurate. The winds are so powerful that they remove huge amounts of material over time. What remains exposed are deeper and hotter layers that ordinary stars usually keep hidden. In many ways, WR102 owes its incredible temperature to these winds. Without them, much of the star's hottest regions would remain buried beneath thicker outer layers. The winds changed everything. To understand how these stellar winds form, we need to look at radiation. Most people think of light as something that illuminates objects. A lamp lights a room. Sunlight brightens a landscape. A flashlight helps you find something under the bed that you probably should have retrieved months ago. Light seems passive, gentle, almost weightless. Yet light carries momentum. Photons may not have mass, but they possess energy and momentum. When enough photons strike matter, they can exert pressure. Normally this pressure is tiny. Near Earth we rarely notice it. Around WR102, however, the situation becomes very different. The star produces extraordinary amounts of radiation. Countless photons stream outward every second. These photons collide with atoms in the star's outer layers. Momentum transfers, pressure builds, material gets pushed outward. The process feeds itself. More radiation creates stronger acceleration. More acceleration creates faster winds. More winds remove additional mass. The result is one of the most powerful stellar outflows known. Imagine standing beside a waterfall. The force of moving water feels impressive. Now imagine replacing every drop of water with particles moving at thousands of kilometers per second. The analogy quickly breaks down because no waterfall on Earth can approach such extremes. Still, it helps illustrate an important point. The stellar wind is not a gentle breeze. It is a torrent of matter driven by enormous energy. Astronomers estimate that Wolf-Rayet winds can reach speeds exceeding 2,000 kilometers per second. Some approach even higher values. To appreciate that number, consider Earth's fastest aircraft. Even advanced military jets travel only a tiny fraction of those speeds. The fastest objects humans routinely build are nowhere close. A particle leaving WR102's surface races outward at velocities that make ordinary human transportation seem stationary. If a passenger airplane somehow moved at Wolf-Rayet wind speeds, it could cross entire continents in seconds. The comparison feels absurd because the scales involved are absurd. Nature is operating in a completely different league. One fascinating consequence of these winds is the creation of giant bubbles in space. The region surrounding WR102 is not untouched. The wind constantly interacts with nearby gas and dust. Material gets compressed, shocked, heated, accelerated. Over time, enormous structures can form. Imagine blowing air into a balloon. The air pushes outward, creating an expanding cavity. Wolf-Rayet winds do something similar on a cosmic scale. The star effectively carves out a region around itself. The process takes thousands of years, then tens of thousands, then hundreds of thousands. Gradually the surrounding environment changes. The star reshapes its neighbourhood. This idea reveals something important about massive stars. They do not simply exist within galaxies. They actively influence them. WR102 is not merely a passive object sitting among other stars. It is an agent of change. Its radiation affects surrounding gas. Its winds affect surrounding matter. Its future explosion will affect surrounding space even more dramatically. The star is participating in the ongoing evolution of the Milky Way. That participation extends far beyond light. The winds carry something especially valuable. Elements. Lots of them. Earlier in its life, WR102 fused hydrogen into helium. Later, more advanced fusion processes began. Heavier elements formed, carbon, oxygen, other products of stellar evolution. Normally many of these materials would remain hidden inside the star until its death. Wolf-Rayet winds change that. Material from deeper layers gets transported outward. The star effectively leaks the products of nuclear fusion into space. This turns WR102 into a supplier of raw materials for future generations of stars and planets. Imagine a giant factory continuously producing valuable resources while simultaneously scattering them across an entire region. That image captures part of what is happening. The carbon that eventually becomes part of future planets. The oxygen that future life might breathe. The heavier elements incorporated into new worlds. Some of that material may pass through Wolf-Rayet winds first. In this way, stellar winds become part of a much larger cycle. Matter forms stars. Stars create new elements. Winds distribute those elements. New stars form from enriched material. New planets emerge. The cycle continues. Without massive stars and their winds, the universe would look very different. Chemical complexity would develop more slowly. Planetary systems would contain fewer heavy elements. The ingredients necessary for life would be less abundant. Oddly enough, one of the most violent processes in astronomy contributes directly to the creation of future possibilities. The galaxy benefits from stellar destruction. Another remarkable aspect of Wolf-Rayet winds is their persistence. Earth's weather changes constantly. A storm arrives, a storm leaves. Wind speeds rise and fall, conditions shift. WR102 does not operate that way. Its wind continues year after year, century after century, millennium after millennium. The star remains locked in a long-term process of mass loss. There is no calm season, no quiet winter, no temporary pause. The outflow simply continues. From the perspective of the star, this mass loss becomes a defining characteristic. Imagine carrying a backpack and removing 1 grain of sand every second. Initially, the change would seem insignificant. After enough time, however, the backpack would empty. WR102 experiences a similar process on a vastly larger scale. The losses accumulate. The star gradually transforms. The future changes because of it. In fact, many astronomers believe the winds play a major role in determining how Wolf-Rayet stars eventually die. Mass influences fate. The amount of material remaining near the end affects what happens next. Will the star explode in a particular way? Will it leave behind a neutron star? Will it collapse into a black hole? The answers depend partly on how much mass survives until the final stages. The winds help determine that outcome. In a very real sense, WR102 is shaping its own future through the material it loses today. The relationship becomes even more interesting when we consider energy. The wind itself contains tremendous kinetic energy. Every particle accelerated outward carries momentum. Every stream of escaping matter transports energy into surrounding space. The cumulative effect is enormous. This energy heats nearby regions, drives shock waves, influences interstellar clouds, changes the behavior of surrounding material. Once again, WR102 reveals itself as more than a simple star. It behaves like a powerful engine continuously injecting energy into its environment. The farther astronomers studied Wolf-Rayet stars, the more they realized these objects occupy a unique position in stellar evolution. They are transitional, temporary, unstable in a cosmic sense. Their winds are not merely interesting side effects. They are signs that major changes are underway. The star is approaching the end of one stage and moving toward another. Everything about the wind reflects that reality. The intensity, the speed, the mass loss, the exposure of deeper layers, all of it points toward the same conclusion. WR102 is living through one of the most dramatic periods a star can experience. At first glance, WR102 looks unstoppable. It shines with extraordinary intensity. Its temperatures rank among the highest known for any star. Its stellar winds race into space at astonishing speeds. Its energy output dwarfs anything humanity has ever produced. Everything about the star seems powerful, victorious even. Yet appearances can be misleading. Beneath all that brilliance lies a surprising truth. WR102 is not winning a battle. It is losing one. Slowly, relentlessly, and inevitably. In fact, many of the very features that make WR102 so impressive are actually signs that the star is approaching the end of its life. The intense heat, the violent winds, the exposed layers, the extraordinary radiation. These are not indicators of eternal strength. They are symptoms of a star consuming itself. Astronomy often reveals a curious pattern. The most spectacular objects tend to be living on borrowed time. Massive stars burn brightest because they spend fuel fastest. The universe allows tremendous power, but it rarely allows that power to last. WR102 is one of the clearest examples of this principle. To understand why, imagine a giant warehouse filled with fuel. If the fuel is consumed carefully, the warehouse might supply energy for decades. If the fuel is burned recklessly, the supply disappears much faster. Stars follow similar rules. The Sun burns hydrogen at a relatively measured pace. Its fuel reserves are enormous. Its consumption rate is modest compared with more massive stars. As a result, the Sun enjoys remarkable longevity. WR102 operates very differently. From the beginning of its life, it has consumed fuel aggressively. Its enormous mass created extraordinary pressures inside the core. Those pressures created extraordinary temperatures. Those temperatures accelerated fusion. Fusion released huge amounts of energy. The star became incredibly luminous. The process sounds impressive because it is impressive, but there is a hidden cost. Every fusion reaction consumes fuel. Every second of brilliance uses resources that can never be recovered. Stars do not refill their tanks. There are no cosmic fuel stations waiting nearby. Everything a star will ever have is largely determined at birth. The future depends on how efficiently that fuel is used. WR102 has never been interested in efficiency. It burns with intensity, and intensity comes with consequences. Millions of years ago, the star contained significantly more mass than it does today. The difference wasn't small. Wolf-Rayet stars can lose enormous amounts of material throughout their evolution. The stellar winds we discussed earlier are not merely carrying away a few stray particles. They're removing substantial portions of the star itself. Imagine waking up every morning slightly smaller than the day before. Not enough to notice immediately, but enough that after years the difference becomes impossible to ignore. That is essentially what WR102 has been experiencing. The process is slow from a human perspective. Yet on stellar timescales, it is dramatic. Material leaves the star continuously. The star grows lighter. The structure changes. Its future shifts, and there is no way to stop it. Gravity plays an important role in this story. Throughout a star's life, gravity remains patient. Fusion may dominate for millions of years. Radiation may flood outward. Stellar winds may rage. The star may appear powerful and secure, Gravity waits, always. The moment fusion begins weakening, gravity notices. The balance that maintained the star starts changing. This balance is worth examining carefully because it determines everything. Stars exist because two opposing forces remain roughly equal. Gravity pulls inward, pressure pushes outward. As long as both forces remain balanced, the star survives. For most of a star's life, fusion provides the outward pressure. Hydrogen becomes helium, energy is released, the core remains supported, gravity remains frustrated, the star continues shining. But hydrogen cannot last forever. Eventually reserves become depleted. When that happens, stars adapt. New fusion processes begin. Helium starts fusing. Later, heavier elements may appear. The star continues surviving by changing the fuel source. Massive stars excel at this process. They progress through multiple stages of nuclear burning: carbon, neon, oxygen, silicon. Each stage produces new elements. Each stage keeps gravity temporarily under control. Yet there is a catch. Every new fuel source burns faster than the previous one. This is one of the strangest facts in stellar evolution. The star works harder and harder simply to remain alive. Imagine a business that needs increasing amounts of money every month just to stay open. At first, the costs are manageable. Later, they become overwhelming. The same thing happens inside massive stars. Hydrogen burning can last millions of years. Helium burning lasts less time. Subsequent stages become progressively shorter. Eventually, some phases may last only years, or months, or even days. The closer a massive star moves toward its end, the faster events unfold. UR-102 has already travelled far down that road. Its current state tells astronomers that much of its original fuel has already been consumed. The star is not at the beginning. It is not even comfortably in the middle. It is approaching the later stages of a very intense life. This is one reason Wolf-Rayet stars attract so much scientific interest. They provide a glimpse of what happens when massive stars near the end of their journey. Astronomers are essentially watching advanced stellar evolution in progress. The exposed layers reveal evidence of earlier fusion. The winds reveal ongoing mass loss. The temperature reveals extraordinary conditions. Every observation tells part of the same story. The star is changing, and those changes are accelerating. There is something almost paradoxical about WR-102. The hotter it becomes, the closer it moves toward destruction. The more impressive its energy output appears, the less time it may have remaining. To human intuition, that feels backwards. We often associate strength with survival. In stars, extreme power can indicate the opposite. Imagine a candle. A small flame burns steadily for hours. Increase the flame dramatically and the candle disappears much faster. The brighter flame looks stronger. In reality, it is consuming itself more rapidly. WR-102 follows a similar principle. Its tremendous output comes at a cost. Fuel disappears faster, mass disappears faster, time disappears faster. Everything about the star's existence has become accelerated. The stellar winds contribute to this process in an important way. Every particle carried away by the wind represents lost mass. Lost mass alters the future. Mass determines gravity. Gravity determines pressure. Pressure influences fusion. Fusion influences evolution. The entire system is interconnected. Remove enough material and the star's fate changes. Astronomers spend considerable effort trying to estimate these effects. How much mass has already been lost? How much remains? How quickly is the loss continuing? The answers help predict what will happen later. Even with modern technology, however, certainty remains difficult. Stars are complex. Wolf-Rayet stars are especially complex. The details matter. Small differences can influence outcomes. Yet one conclusion remains clear. WR-102 cannot remain in its current state forever. No Wolf-Rayet star can. The phase is temporary by nature. The winds guarantee change. The fusion processes guarantee change. The passage of time guarantees change. Eventually, the star will reach a point where no further adjustments remain available, and when that moment arrives, gravity begins winning. Perhaps the most fascinating part of this story involves the star's core. Everything visible from outside represents only part of the picture. The real drama unfolds deep inside. There, nuclei continue colliding. Fusion continues creating heavier elements. Pressure remains immense. Temperatures remain extraordinary. The core behaves like an engine operating under incredible conditions. Yet unlike a machine, the core cannot be repaired. It cannot receive maintenance. It cannot replace worn components. It simply continues operating until physics says otherwise. Every second, the core moves closer to a critical threshold. For most of the star's life, fusion generated enough energy to resist collapse. That resistance will not last forever. There is an ultimate limit, a point beyond which further fusion no longer helps, a point where the star runs out of useful options. When astronomers study WR102, they are not merely examining a hot star, they are observing a future catastrophe in preparation. That sounds dramatic, but it is also accurate. The star's current appearance is part of a larger sequence. Every stage leads naturally to the next. The winds remove mass, the core evolves, the fuel changes, the structure transforms. The future approaches. Nothing occurring today is random. Everything fits within a long chain of stellar evolution. And yet there is something oddly beautiful about that process. Not because destruction itself is beautiful, rather because it reveals how dynamic the universe really is. Stars are not permanent landmarks, they are temporary events, long-lived events by human standards certainly. But temporary nonetheless. The night sky often feels timeless. The stars seem eternal. Objects like WR102 remind us otherwise. Even the mightiest stars change. Even the hottest stars evolve. Even the most powerful stars eventually reach limits. The universe is full of motion and transformation. Nothing remains exactly the same forever. UR102 simply makes that reality easier to see. The star's extraordinary heat, its immense winds, its exposed layers, its remarkable brightness. All of these qualities point toward the same conclusion. The star is living through one of the final major stages of its existence. It is still magnificent, still powerful, still capable of reshaping its surroundings. But beneath that power lies a countdown, not one measured in human years, not one visible on a clock. A stellar countdown measured through fuel consumption, mass loss, and the gradual advance of physics toward an unavoidable outcome. Eventually, WR102 will run out of ways to resist gravity. Eventually, the balance maintaining the star will fail. Eventually, one of the hottest stars in the universe will face its final transformation. And when we compare WR102 to our own sun, the scale of that transformation and the extraordinary nature of this star's life becomes even easier to understand. Take a moment and think about the sun. Not as an abstract astronomical object, not as a glowing sphere floating somewhere in space. Think about it as part of your daily life. The reason mornings exist, the reason plants grow, the reason oceans remain liquid, the reason Earth is not a frozen ball drifting through darkness. The sun feels ordinary largely because it is familiar. It rises every day. It has always been there. Most of us rarely stop to consider just how extraordinary our star actually is. And yet, compared with WR102, the sun begins to look surprisingly modest. This isn't a criticism of the sun. The sun is an excellent star, reliable, long-lived, exceptionally helpful if you happen to enjoy breathing, but astronomy has a way of introducing objects so extreme that even familiar cosmic giants seem almost restrained by comparison. WR102 is one of those objects. To appreciate just how unusual this star really is, let's place it beside the object we know best. The comparison starts with temperature. The Sun's visible surface sits at approximately 5,500 degrees Celsius. That number is already difficult to comprehend. Steel melts long before reaching those temperatures. Most materials we encounter in everyday life would not survive even brief exposure. From a human perspective, the Sun is unimaginably hot. WR102, however, reaches temperatures estimated around 200,000 degrees Celsius. The difference is staggering. This is not a small improvement, not a doubling, not even a tenfold increase. WR102's surface temperature exceeds the Sun's by an enormous margin. Imagine comparing a gentle campfire to an industrial furnace. Then imagine discovering that the furnace itself is being compared to something even more powerful. Eventually, comparisons stop feeling useful. The numbers simply become too large. Yet temperature alone tells only part of the story. Stars are complicated. A star's influence depends on many factors: mass, size, luminosity, radiation, composition, evolutionary stage. All contribute to the final picture. And when we compare WR102 to the Sun across those categories, the differences become fascinating. Let's start with age. The Sun is roughly 4.6 billion years old. That's an astonishing length of time. When the Sun formed, Earth itself was still taking shape. Entire geological eras have come and gone beneath its light. Dinosaurs appeared. Dinosaurs vanished. Human civilization emerged only within the tiniest fraction of the Sun's lifetime. Even more remarkable, the Sun is only about halfway through its primary life. It still has billions of years remaining. WR102 tells a completely different story. Although massive stars begin life with far more fuel, they consume that fuel at astonishing rates. Instead of surviving for billions of years, some massive stars live only a few million years. Imagine receiving a bank account with vastly more money than your neighbour. Then imagine spending it thousands of times faster. Suddenly the advantage disappears. Massive stars behave similarly. Their tremendous energy output burns through resources rapidly. WR102 lives intensely, the Sun lives patiently. The contrast could hardly be greater. This difference highlights one of the most surprising truths in astronomy. Bigger stars often die sooner. Human intuition expects the opposite. Larger fuel reserves should last longer. Nature disagrees. Extreme mass creates extreme consumption. The result is a shorter life. Another major difference involves stability. The Sun is remarkably stable. Of course, it experiences solar flares. Sunspots appear and disappear. The solar wind flows continuously. Yet on the whole, the Sun behaves predictably. Life on Earth depends on that predictability. If the Sun varied dramatically from year to year, our planet would become a much more difficult place to inhabit. WR102 exists much closer to the edge. Its powerful stellar winds continuously strip material away. Its outer layers have largely vanished. Its internal evolution has advanced significantly. The star is no longer in the comfortable middle years of stellar life. It is approaching its final stages. Imagine two people. One is enjoying a calm afternoon stroll through a park. The other is sprinting uphill carrying a backpack full of bricks. Both are moving. But they are experiencing very different realities. The Sun resembles the walker. WR102 resembles the sprinter. This brings us naturally to one of the most entertaining thought experiments in astronomy. What would happen if WR102 suddenly replaced our Sun? The short answer is simple: nothing good. The slightly longer answer is much more interesting. First, let's establish one important detail. WR102 is not physically large enough to swallow Earth's orbit immediately. People often imagine giant stars expanding until they consume entire planetary systems. Some stars certainly do become enormous. WR102's danger comes primarily from temperature and radiation rather than sheer size. That distinction matters. Earth would not vanish instantly inside the star. The situation would somehow be worse. Let's imagine that overnight, through some impossible cosmic magic, WR102 appears exactly where the Sun currently sits. The first thing humanity would notice would be brightness, an overwhelming brightness. The sky would transform immediately. Daylight would become something entirely different. The amount of radiation reaching Earth would increase dramatically. Within moments, the planet's energy balance would collapse. Temperatures would begin rising rapidly. Oceans would start heating. Atmospheric chemistry would begin changing. Life would find itself facing a crisis unlike anything in Earth's history. And this would happen very quickly. The Sun currently provides just the right amount of energy to maintain liquid water across much of Earth's surface. That balance is delicate. Even relatively small changes can affect climate. WR102 would not represent a small change. It would represent a catastrophe. The additional energy reaching Earth would be enormous. Surface temperatures would climb relentlessly. The oceans would begin evaporating, cloud systems would transform, the atmosphere would fill with water vapour. Ironically, water vapour is also a greenhouse gas. As more entered the atmosphere, additional warming would occur. The process would feed upon itself. Scientists sometimes refer to this kind of scenario as a runaway greenhouse effect. Earth would essentially lose control of its climate. The planet would become increasingly hostile. Eventually the oceans themselves would disappear. Imagine all of Earth's oceans, the Atlantic, the Pacific, the Indian Ocean, every sea, every lake, every river. Now imagine them gradually turning into atmospheric vapour. The scale of the transformation is difficult to comprehend. Yet under the influence of WR102, that outcome becomes unavoidable. As temperatures continued rising, another problem would emerge: radiation. Remember that WR102 emits tremendous amounts of ultraviolet radiation. Far more than the Sun, Earth's atmosphere protects us from much of the ultraviolet radiation produced by our current star. That protection works because the atmosphere and ozone layer absorb significant portions of incoming energy. Under WR102, those protective systems would be overwhelmed. Atmospheric chemistry would begin changing dramatically. The ozone layer would suffer severe damage. Surface conditions would become increasingly hostile. Living organisms would face intense radiation exposure. The effects would be devastating. Plants would struggle. Marine ecosystems would collapse. Food chains would unravel. Entire biological systems would begin failing. And this is before we even consider the stellar wind. The solar wind influences Earth today, but our magnetic field provides significant protection. Auroras are beautiful evidence of that interaction. WR102's stellar wind operates on a completely different scale. The outflow carries vastly more energy, vastly more momentum, vastly more danger. Earth's magnetic field would face an assault unlike anything in its history. Particles would bombard the planet continuously. Atmospheric erosion could become significant. Radiation exposure would increase further. Technology would suffer. Satellites would fail. Electrical systems would struggle. Modern civilization would face challenges so extreme that survival itself would become uncertain. At this point, Earth would already be doomed. Yet WR102 still has more surprises, because replacing the Sun isn't merely a question of present conditions, it is also a question of future conditions. The Sun is expected to remain relatively stable for billions of years. WR102 does not offer that luxury. Its future contains something much more dramatic. A massive star approaching the end of its life eventually faces collapse, and collapse leads to explosion. One day, WR102 is expected to die. When it does, the event will likely be spectacular. The exact details remain uncertain, but the outcome will almost certainly involve tremendous violence. If such an explosion occurred at the distance of Earth's orbit, there would be little left to discuss afterward. The solar system itself would be transformed. Fortunately, reality remains much kinder. WR102 resides thousands of light years away. Its radiation cannot harm us. Its winds cannot reach us. Its eventual death poses no threat to Earth. Astronomers can study it safely from afar. The thought experiment works precisely because distance protects us. Distance is one of the universe's most underrated safety features. Many of the cosmos's most dangerous objects appear harmless simply because they are extraordinarily far away. Black holes, neutron stars, supernovae, Rayet stars, all can be studied comfortably because immense distances separate them from us. Remove that distance and the story changes immediately. Still, there is another side to this comparison. For all its apparent modesty, the Sun may actually be the better star. Not the hotter star, not the more powerful star, not the more dramatic star, the better star for supporting life. The Sun burns steadily. It evolves slowly. It provides stable energy. It gives lifetime to develop, time to adapt, time to flourish. WR102 offers none of those advantages. Its intensity creates excitement for astronomers. It would create disaster for planets hoping to nurture life. In a strange way, comparing WR102 with the Sun teaches us something important about our place in the universe. We often assume bigger means better. Astronomy repeatedly demonstrates otherwise. The most extreme stars are not necessarily the most useful. The hottest stars are not necessarily the most desirable. The universe's greatest powerhouses can also be its least hospitable environments. WR102 represents one of nature's most extraordinary stellar achievements. The Sun represents something different: balance, stability, longevity. Both are remarkable, but only one allows oceans, forests, cities, and sleepy science videos to exist. And while imagining WR102 in place of the Sun helps reveal just how extreme this star truly is, another question naturally follows. If stars this powerful burn through their lives so quickly, what does that tell us about the lives of giant stars in general? And why do the universe's most magnificent stars often end up having the shortest lifespans of all? When we look at the night sky, it is easy to assume that bigger stars must have easier lives. After all, bigger usually sounds better. A larger fuel supply should last longer. Greater mass should provide greater stability. More resources should create greater endurance. That logic works well enough in many parts of everyday life. A larger fuel tank allows a car to travel farther. A larger warehouse can store more supplies. A larger reservoir can hold more water. Stars, however, obey a different set of rules. In the universe, size often comes with a price, and nowhere is that more obvious than among the giant stars that eventually become objects like WR102. The biggest stars are often the shortest lived. The most powerful stars frequently have the briefest careers. The brightest stars are sometimes the fastest to disappear. At first, that sounds completely backwards, yet it is one of the most important lessons in stellar evolution. To understand why, imagine two fires. One is a small candle, the other is an enormous bonfire. Which one consumes fuel faster? The answer is obvious. The bonfire may contain more fuel initially, but it burns through that fuel at a much greater rate. The candle survives because it burns slowly. The bonfire impresses everyone nearby but pays for that spectacle with rapid consumption. Massive stars behave in much the same way. The Sun is relatively conservative. It burns hydrogen steadily. It manages its fuel carefully. Its energy output remains remarkably stable. As a result, it enjoys a lifespan measured in billions of years. WR102 and stars like it are the opposite. From the moment they form, they begin living at extraordinary intensity. The reason starts with gravity. Massive stars possess enormous amounts of mass. That statement sounds obvious, but the consequences are profound. More mass means stronger gravity. Stronger gravity creates greater compression inside the core. Greater compression creates higher temperatures. Higher temperatures accelerate fusion. Fusion releases more energy. The star becomes brighter. But brightness is not free. Every increase in energy output requires additional fuel consumption. The star effectively spends its future faster. Imagine two people receiving identical bank accounts. One spends a few dollars each day, the other spends thousands. The second person may appear wealthier initially, but the account empties much faster. Massive stars face the same problem. Their immense energy output requires immense fuel consumption. As a result, their lives become surprisingly short. Let's consider some numbers. The Sun is expected to spend roughly 10 billion years in its main hydrogen-burning phase. That is an almost incomprehensible amount of time. Human civilization occupies only a tiny fraction of it. Even recorded history barely registers against such scales. A truly massive star may spend only a few million years in the equivalent phase. Millions of years still sound substantial, yet compared with billions, they are astonishingly brief. It's the difference between a long novel and a single paragraph. The star rushes through evolutionary stages that smaller stars experience much more slowly. This accelerated life creates fascinating consequences. One of them is constant change. Massive stars rarely remain in one state for long. Their internal structures evolve rapidly. Their fuel sources change, their temperatures shift. Their outer layers respond. The entire star becomes a dynamic system undergoing continuous transformation. The Sun changes too, of course. All stars do. But many of the Sun's changes occur so gradually that human civilizations never notice them. Massive stars evolve on timelines that astronomers can study much more directly. The changes remain slow by human standards, but rapid by stellar standards. In many ways, giant stars spend their lives sprinting through evolutionary stages. The process begins with hydrogen fusion. Like most stars, massive stars initially generate energy by fusing hydrogen into helium. During this phase, gravity and pressure remain balanced. The star shines brilliantly. Everything appears stable, yet beneath the surface, a clock is already ticking. Hydrogen reserves steadily decrease. Eventually, the core becomes dominated by helium. At that point, new challenges emerge. The star must adapt or collapse. Fortunately for massive stars, adaptation is possible. The core contracts. Temperatures rise further. Helium fusion begins, new elements form, energy production continues. Gravity remains temporarily controlled. The star survives. But notice something important. Each new stage requires more extreme conditions. Hydrogen fusion is relatively easy by stellar standards. Helium fusion demands higher temperatures. Subsequent fusion processes demand even more. As evolution continues, the star works harder simply to remain alive. Imagine riding a bicycle uphill. The climb becomes steeper. More effort is required, then steeper still. Eventually, maintaining the same speed becomes exhausting. Massive stars face a similar challenge. Every evolutionary stage requires greater internal extremes. The reward is temporary survival. The cost is accelerating fuel consumption. This leads to one of the most remarkable aspects of giant stars. The later stages of their lives become progressively shorter. Hydrogen burning may last millions of years. Helium burning lasts less. Carbon burning lasts less still. The timeline shrinks dramatically. Astronomers sometimes describe the final stages almost like a countdown. The closer the star moves toward collapse, the faster events unfold. The effect can be startling. A massive star may spend millions of years burning hydrogen, then hundreds of thousands burning helium, then progressively shorter intervals for subsequent stages. Eventually, certain fusion phases may last only years, or months, or days. Imagine reading a book where the first chapters span hundreds of pages, while the final chapters become shorter and shorter, until the conclusion arrives in a rush. Massive stellar evolution often works that way. WR 102 has already reached an advanced point in this process. Its exposed layers provide evidence of earlier evolutionary stages. Its winds reveal ongoing mass loss. Its temperature reveals extraordinary conditions. Everything about the star suggests that it has travelled far from its youthful beginnings. The journey has been fast, the journey has been intense, and the journey continues. Another reason giant stars experience such dramatic lives involves instability. The larger a star becomes, the more difficult balance becomes. Gravity increases, radiation pressure increases, internal temperatures increase, competing forces become more extreme. Maintaining equilibrium becomes harder. The star constantly adjusts, expands, contracts, loses mass, changes structure. The result is a life that feels far less tranquil than that of smaller stars. Massive stars are often described as unstable because they operate so close to physical limits. Small changes can produce significant consequences. This instability contributes directly to the formation of Wolf-Rayet stars. The intense radiation generated inside massive stars helps drive powerful stellar winds. Those winds remove material. Removing material alters the star's structure. The altered structure changes future evolution. Everything becomes interconnected. The star is effectively reshaping itself while racing toward its eventual fate. There is something almost tragic about this process. The qualities that make giant stars spectacular also guarantee their downfall. Their enormous mass creates extraordinary luminosity. That luminosity drives extraordinary fuel consumption. Fuel consumption accelerates evolution. Accelerated evolution shortens life. The star's greatest strength becomes its greatest weakness. And yet without these stars, the universe would be a very different place. Massive stars perform essential work. Their cores create heavy elements. Their winds distribute those elements. Their eventual explosions scatter them even farther. Many of the atoms necessary for planets and life originate inside giant stars. The carbon in your body, the oxygen you breathe, the calcium in your bones, the iron in your blood. These elements were forged through stellar processes. Some owe their existence directly to massive stars. This creates a fascinating paradox. The shortest-lived stars often leave the greatest legacy. The Sun may outlive WR102 by billions of years, yet WR102 contributes materials that influence future generations of stars and planets. Its life is brief. Its impact is enormous. Astronomers sometimes compare stellar evolution to ecology. Individual organisms may live short lives. Entire ecosystems endure. Similarly, individual stars come and go. Galaxies continue evolving. The material from one generation becomes the foundation for the next. WR102 participates in that cycle right now. Its winds carry enriched material outward. Its future explosion will distribute even more. The star is helping shape environments it will never see. Future stars may form from gas influenced by WR102. Future planets may contain atoms forged inside WR102. Future life may depend upon elements created inside WR102. The star's death contributes to future creation. That relationship appears repeatedly throughout astronomy. Destruction and creation often occur together. One process enables the next. Massive stars illustrate this beautifully. Their lives are short. Their deaths are violent. Their contributions are immense. Perhaps that is why astronomers find them so captivating. These stars reveal the universe operating at maximum intensity. Nothing is modest, nothing is gradual, everything feels amplified. The temperatures, the luminosities, the winds, the transformations, the eventual endings. WR102 embodies all of those qualities. It exists as a reminder that the universe is not always patient. Sometimes nature chooses speed over longevity. Sometimes it chooses intensity over endurance. Sometimes it creates stars that burn with such extraordinary power that their entire lives become compressed into a cosmic instant. Yet for all their drama, giant stars still follow the same fundamental laws as every other star. Gravity pulls inward, fusion pushes outward, fuel is consumed, time passes, the details change, the scale changes, the intensity changes, the underlying principles remain. And those principles lead every massive star toward the same inevitable question. What happens when the fuel finally begins running out? Far out in the Milky Way, WR102 continues doing what it has done for millions of years. It shines, it loses mass, it drives powerful stellar winds into surrounding space, it converts lighter elements into heavier ones deep within its interior. From a human perspective, the star appears permanent. If you could somehow observe it every night for an entire lifetime, it would seem unchanged. Generation after generation could pass beneath the sky, while WR102 continued glowing. This apparent permanence is one of astronomy's greatest illusions. Stars feel eternal because human lives are short. The universe operates on very different timescales. What appears stable to us is often temporary when viewed across millions of years. WR102 is no exception. In fact, everything astronomers know about this star suggests that its future contains one of the most dramatic events nature can produce. A stellar death. Not the quiet fading experienced by smaller stars. Not a gradual disappearance. Something far more violent. The reason lies deep inside the star. Throughout this journey we've discussed gravity and fusion repeatedly, because those two forces determine nearly everything that happens during a star's life. Fusion pushes outward, gravity pulls inward. The balance between them keeps the star alive. As long as fusion continues generating enough pressure, collapse remains temporarily prevented. The key word there is temporarily. No star possesses an infinite fuel supply. Eventually every star reaches a point where options begin running out. For a star like the Sun, that process unfolds relatively gently. The Sun will eventually become a red giant. Its outer layers will expand. Later, those layers will drift away. A white dwarf will remain. The transformation will be enormous, but it will not involve a catastrophic explosion capable of disrupting large regions of the galaxy. WR102 belongs to a completely different category. Massive stars do not usually retire quietly. They tend to leave the universe with a final act that rivals everything that came before. To understand why, we need to examine what happens inside the core during the final stages of stellar evolution. Early in a star's life, hydrogen fusion dominates. Hydrogen becomes helium. Energy is released. The star remains stable. As hydrogen reserves diminish, the core contracts. Temperatures rise. Helium fusion begins. Later, more advanced stages follow. Carbon, neon, oxygen, silicon. The star progresses through increasingly extreme forms of nuclear burning. Each stage creates heavier elements. Each stage helps resist gravity a little longer. Each stage also becomes shorter. The closer the star moves toward its end, the faster events unfold. For a massive star, the core eventually begins producing iron. At first glance, that might not sound especially important. Iron seems familiar, ordinary, common. Many everyday objects contain it. Yet in stellar physics, iron represents a major turning point. The reason involves energy. Fusion normally releases energy. Hydrogen fusion releases energy. Helium fusion releases energy. The same pattern continues through progressively heavier elements. Iron changes the rules. Fusing iron does not release energy in the same way. Instead, it consumes energy. This creates a problem. Actually, it creates a catastrophe. The star's entire existence depends on fusion generating enough pressure to oppose gravity. Once the core becomes dominated by iron, that support system begins failing. Imagine a massive building supported by countless pillars. One by one, those pillars disappear. The structure may remain standing briefly. Eventually, however, collapse becomes unavoidable. Something similar happens inside massive stars. Gravity has been waiting patiently for millions of years. Fusion kept pushing back. Iron removes fusion's advantage. Gravity finally gets an opportunity, and gravity never wastes opportunities. Once core support disappears, collapse begins. The process is astonishingly fast. A star that spent millions of years evolving can experience core collapse in seconds. That contrast is one of the most remarkable things in astronomy. The longest stages occupy millions of years. The final transition happens almost instantly. The core contracts violently. Densities increase dramatically. Temperatures soar. Matter becomes compressed to extraordinary levels. The entire structure of the star changes. At some point, the collapsing core becomes so dense that further compression becomes difficult. The inward-moving material slams into this compressed region. A shock wave forms. Energy surges outward. The star explodes. Astronomers call this event a core collapse supernova. The name sounds technical. The reality is breathtaking. For a brief period, a single exploding star can outshine entire galaxies. Think about that for a moment. A galaxy may contain hundreds of billions of stars, yet one supernova can temporarily rival all of them combined. The amount of energy released is difficult to comprehend. The explosion floods space with radiation. Shock waves race outward. Heavy elements are scattered across surrounding regions. The star's life ends. A new phase begins. If WR102 follows this path, the event will be spectacular. Fortunately, it is also extremely distant. Thousands of light years separate us from the star. That distance protects Earth completely. Even a future supernova would be a scientific event rather than a threat. Astronomers would celebrate. Telescopes would turn toward the explosion. Researchers would gather data eagerly. The night sky might gain an unusually bright object. Life on Earth would continue normally. Distance once again proves itself to be one of the universe's greatest safety features. Still, the explosion itself raises an important question. What remains afterward? Stars do not simply vanish. Something survives. The answer depends largely on mass, and this brings us to one of the most fascinating possibilities surrounding WR102. Could it become a black hole? The short answer is yes. In fact, many astronomers consider that outcome entirely plausible. To understand why, imagine the collapsing core after the supernova. The outer layers have been blasted away. The explosion has occurred. The remaining core faces gravity alone. Its future depends on how much mass remains concentrated in that region. If the core falls within a certain mass range, it becomes a neutron star. Neutron stars are extraordinary objects. A single teaspoon of neutron star material would weigh billions of tons on Earth. The densities involved are almost unimaginable, yet neutron stars still possess a surface. They still exist as physical objects. Gravity wins dramatically, but not completely. Black holes represent the next step. If the remaining core is massive enough, gravity overwhelms every known form of resistance. Collapse continues. Matter becomes compressed beyond familiar limits. An event horizon forms. A black hole is born. At that point, gravity becomes so powerful that not even light can escape. The object effectively disappears from direct view. Its presence can still be detected through gravitational effects, but the black hole itself remains hidden. This possibility makes WR102 especially intriguing. The star began life with enormous mass. Even after millions of years of mass loss, substantial material may remain. Astronomers continue studying Wolf-Rayet stars partly because they appear to be likely black hole progenitors. In simpler terms, they may represent the final visible stage before black hole formation. That idea is extraordinary. When we observe WR102 today, we may be looking at a future black hole in preparation. The star exists in a transitional state. It remains visible. It remains active. It continues shedding mass and generating tremendous energy. Yet somewhere in its future lies a dramatic transformation. The brilliant star we see today may eventually become one of the darkest objects in the universe. There is something strangely fitting about that possibility. WR102 already pushes physical limits. Its temperatures rank among the highest known. Its winds rank among the strongest known. Its evolutionary stage represents one of the most extreme phases of stellar life. A future black hole would feel like a natural continuation of that story. The star began as an exceptional object. It may end as an exceptional object as well. Of course, astronomers remain careful. Nature does not always follow the simplest predictions. Mass loss complicates matters. The precise structure of the core matters. Rotation matters. Magnetic fields may matter. Small differences can influence outcomes. This is why researchers continue studying Wolf-Rayet stars so intensely. Each observation improves understanding. Each measurement refines predictions. The future of WR102 remains uncertain in detail, even if the broad outline appears clear. Something dramatic will happen. The star will not remain as it is forever. Gravity guarantees that. The real question concerns exactly how the final act unfolds. Will the supernova be unusually energetic? How much mass will remain afterward? Will a neutron star survive? Will a black hole form? Those questions continue driving research today. Yet perhaps the most remarkable aspect of the story is not the explosion itself. It is what the explosion accomplishes. Right now, as you listen to this, there are atoms inside your body that were created long before Earth existed, long before the sun formed, long before oceans appeared, long before the first living cell emerged on our planet. In fact, some of those atoms may be older than our entire solar system. That statement sounds almost unbelievable. After all, when we think about ourselves, we usually think about birthdays, years, perhaps decades, maybe a century if we're feeling optimistic. Atoms operate on very different timelines. The carbon in your body may have travelled through multiple generations of stars. The oxygen you breathe may have originated inside a giant stellar furnace billions of years ago. The calcium in your bones may have been forged in conditions so extreme that no laboratory on Earth could reproduce them. And somewhere within that story, stars like WR102 play an important role. One of the most fascinating discoveries in astronomy is that stars are not simply sources of light. They are factories, element factories. The universe we see today would not exist in its current form without them. Planets would be different, life would be different, even chemistry itself would be different. To understand why, we need to travel back to the beginning. Not the beginning of WR102, not even the beginning of the Milky Way, the beginning of the universe itself. When the universe first emerged from the Big Bang, it was surprisingly simple. People often imagine the early universe as containing everything we see today. Galaxies, stars, planets, complex elements. The reality was much less complicated. The young universe consisted mostly of hydrogen and helium. A tiny amount of lithium existed as well, and that was largely it. No oxygen, no carbon, no nitrogen, no iron, no calcium, no gold, no silicon. None of the ingredients required for rocky planets and living organisms. The universe contained energy and simple matter. The rest had to be created later. This presents an interesting question. If the early universe lacked those elements, where did they come from? The answer is stars. Stars spent billions of years acting as cosmic manufacturing plants. Inside their cores, nuclear fusion gradually transformed simple elements into more complex ones. In many ways, stellar evolution is also chemical evolution. Every stage of a star's life changes the universe's inventory. The process begins with hydrogen. Hydrogen is wonderfully simple. One proton, one electron, that's all. It is the most abundant element in the cosmos. Stars spend much of their lives turning hydrogen into helium. This process powers stars. It produces energy. It keeps gravity under control. For many stars, hydrogen fusion defines most of existence. But massive stars have ambitions beyond helium. Because their cores become much hotter and much denser, additional fusion processes become possible. Helium begins fusing into heavier elements. Carbon appears, oxygen appears, neon appears, magnesium appears. The list continues growing. The star becomes a chemical workshop operating under extraordinary conditions. Imagine an enormous factory receiving simple raw materials and gradually transforming them into increasingly sophisticated products. Massive stars do something similar. The difference is that their machinery consists of gravity, pressure, and nuclear physics. The products eventually become the building blocks of worlds. WR102 represents a particularly advanced stage in this story. The star has already progressed far beyond simple hydrogen burning. Its exposed layers reveal products of earlier fusion stages. Materials forged deep within the star have become visible because stellar winds removed outer layers. Astronomers studying WR102 are not merely observing a hot star. They are observing a place where the chemistry of the universe is actively being transformed. That transformation matters enormously. Let's consider carbon for a moment. Every known life form on Earth depends on carbon. The molecules responsible for biology are built around it. Proteins, DNA, sugars, fats. Countless biological structures rely on carbon's unique chemical properties. Without carbon, life as we know it becomes difficult to imagine. Yet the early universe contained essentially none of it. Carbon had to be manufactured. Stars performed the job. Deep within massive stellar cores, helium nuclei collide and combine. The process eventually creates carbon. Every carbon atom on Earth has a stellar history. Every carbon atom in your body originated somewhere inside a star. You are literally carrying ancient stellar material around with you. The same is true for oxygen. Oxygen feels ordinary because it surrounds us. We breathe it constantly. Forests release it. The atmosphere contains it. Yet oxygen did not exist in abundance when the universe was young. Stars created it. Massive stars proved especially effective. Inside stellar cores, fusion reactions gradually assembled oxygen from lighter ingredients. Over time, stellar winds and stellar explosions distributed that oxygen throughout galaxies. Future generations of stars inherited it. Future planets inherited it. Earth inherited it. Eventually you inherited it. This realization changes how we think about ourselves. The atoms making up your lungs were not manufactured on Earth. The atoms making up your blood were not manufactured on Earth. Earth assembled them. But their origin lies elsewhere. Their true birthplace was inside stars. Astronomer Carl Sagan famously described humans as star stuff. The phrase became popular because it captures something important. It is not poetry. It is chemistry. It is physics. It is literally true. The elements inside us were forged through stellar processes. WR102 belongs to that same grand tradition. Another fascinating example involves calcium. Every time you move, calcium helps make that movement possible. Bones contain enormous quantities of it. Teeth contain it. Muscles rely upon it. Yet calcium also originated in stars. At some point, the atoms supporting your skeleton were part of a stellar interior. They existed in an environment far hotter than anything Earth has ever experienced. They survived stellar evolution. They survived interstellar travel. They survived planetary formation. Eventually they became part of you. The journey is almost impossible to visualize, yet every atom carries that history. Iron tells a similar story. Your blood depends on iron. The element plays a critical role in transporting oxygen through the body. Without it, complex life would struggle. Iron also occupies a special place in stellar evolution. As we discussed earlier, iron represents a turning point. Fusion beyond iron becomes increasingly difficult. Massive stars often approach their final collapse when iron accumulates in the core. In a strange way, the same element helping your body function also helps determine the fate of giant stars. The connection between biology and astronomy becomes unexpectedly intimate. We often think of ourselves as separate from the cosmos. The chemistry says otherwise. The materials are shared, the histories are shared, the origins are shared. Wolf-Rayet stars add another layer to this story because they begin distributing these elements before they die. Most stars keep their products hidden. Their outer layers conceal the fusion processes occurring within. WR102 has lost much of that concealment. Its powerful winds carry enriched material into surrounding space. The star is already contributing to future generations, already enriching its region of the galaxy, already participating in cosmic recycling. Imagine a farmer scattering seeds across a field. Some land nearby, some travel farther. Years later, new growth appears. Wolf-Rayet wines perform something vaguely similar. The materials they distribute eventually become incorporated into new systems. Future stars, future planets, future possibilities. The process unfolds slowly. Galaxies evolve across enormous timescales. Yet the principle remains the same. Material moves, matter recycles. The universe continuously reshapes itself. Of course, the greatest contribution may still lie ahead. When WR102 eventually dies, the event will scatter even more material into surrounding space. The explosion will distribute elements forged throughout the star's lifetime. Regions that were once hidden deep inside the core will become part of the wider galaxy. The star's death becomes an act of distribution. One generation ends, the next gains resources. This cycle repeats across the universe, again and again. Stars form, stars evolve, stars create, stars die. Their material returns to space. New stars form from enriched clouds. The process continues. Without this cycle, rocky planets would be rare, complex chemistry would be limited, life would face enormous obstacles, the universe would remain chemically simple. Instead, stars spent billions of years increasing complexity. Each generation added new ingredients. Each generation enriched the galaxy further. By the time the solar system formed, the Milky Way already contained the products of countless earlier stars. Earth inherited that legacy. So did every living thing upon it. There is something wonderfully humbling about that realization. When we study WR102, we often focus on temperatures. The winds, the mass loss, the future supernova. Those subjects are fascinating. Yet perhaps the star's most important contribution involves creation rather than destruction. The elements forged inside it may outlive the star by billions of years. Long after WR102 itself is gone, its material may continue participating in new stories, new planets, new ecosystems, perhaps even new civilizations. The star will disappear, its atoms will not. In a sense, the universe never truly wastes anything. Matter changes form, matter changes location, matter changes purpose, but the atoms themselves continue their journeys. And because WR102 operates at such extreme temperatures, it offers astronomers an opportunity to study some of the most powerful element-producing environments in existence. It is both a star and a glimpse into the chemical history of the cosmos, a reminder that every atom around us once had a very different home. Yet as extraordinary as WR102 appears, it is not the only extreme environment in the universe. Its temperatures are astonishing. Its winds are astonishing. Its future explosion will be astonishing. Even so, astronomy contains objects and events that push conditions even further, which raises an intriguing question. When we compare WR102 with supernova, neutron stars, black holes, and even the early universe itself, where does one of the hottest stars known actually rank among the most extreme places nature has ever created? By this point in our journey, WR102 sounds almost unbeatable. Its surface temperature reaches roughly 200,000 degrees Celsius. Its stellar winds rank among the most powerful known. Its radiation floods surrounding space with extraordinary energy. Its future likely involves a spectacular stellar death. After hearing all that, it would be perfectly reasonable to conclude that WR102 must be the hottest thing in the universe. The reality, as astronomy often reminds us, is slightly more complicated. WR102 occupies a fascinating position among cosmic extremes. It is one of the hottest known stars. That distinction is important. Stars, not necessarily objects, not necessarily environments, not necessarily events. The universe contains many ways to become hot. Some involve stars, others involve phenomena so strange that they make even WR102 seem relatively straightforward. To understand where WR102 truly belongs, we need to compare it with some of the hottest places nature has ever created. And perhaps more importantly, we need to answer a subtle question. What exactly do we mean by hot? At first glance, temperature appears simple. A number gets larger, something gets hotter. Easy enough. The challenge is that different astronomical environments measure temperature in different ways. Sometimes we're talking about the temperature of a star's visible surface. Sometimes we're discussing the temperature of a stellar core. Sometimes we're measuring gas heated by violent collisions. Sometimes we're examining matter spiraling into a black hole. The numbers can become confusing because they describe very different situations. WR102's famous temperature refers primarily to its surface. That distinction matters. When astronomers describe WR102 as one of the hottest known stars, they are talking about the visible layers producing the star's radiation. And in that category, WR102 sits extremely high on the list. Very few stars rival it. Most stars fall far below it. The Sun, as we've discussed, reaches roughly 5,500 degrees Celsius at its surface. Many blue stars achieve temperatures around 20,000 to 40,000 degrees. Even among massive stars, values above 50,000 degrees are considered extraordinary. Then WR102 appears with temperatures approaching 200,000 degrees. Suddenly the scale changes. The star occupies territory that relatively few known objects can match. Yet the moment we stop limiting ourselves to stars, things become much more interesting. Let's begin with a familiar astronomical event, a supernova. When a massive star explodes, temperatures rise dramatically. For a brief period, conditions become far more extreme than those found on WR102's surface. The shockwave generated during a supernova creates temperatures reaching millions or even billions of degrees. Nuclear reactions occur at astonishing rates. Matter is compressed and heated. Elements heavier than iron can form. The environment becomes extraordinarily energetic. If WR102 eventually explodes as a supernova, it will briefly create temperatures far exceeding those it possesses today. This sounds strange at first. How can a star hotter than 200,000 degrees become even hotter? The answer lies in violence. Supernovae are among the most energetic events in the universe. Energy released over millions of years may emerge in a matter of seconds. The resulting conditions push matter into entirely new regimes. Fortunately for surrounding civilizations, such events remain rare and usually very distant. Otherwise, the universe would be a much more hazardous place. Neutron stars offer another fascinating comparison. At first glance, neutron stars seem smaller and less impressive than giant stars. Many measure only around 20 kilometers across. That's smaller than some cities. WR102, meanwhile, dwarfs entire planetary systems. Yet appearances can be deceptive. Neutron stars contain extraordinary amounts of mass compressed into tiny volumes. The resulting densities become almost impossible to imagine. The temperatures shortly after formation can exceed hundreds of billions of degrees. Even after cooling significantly, neutron stars remain among the most extreme objects known. Imagine taking the mass of a star and squeezing it into something the size of a city. The result would not behave like ordinary matter. The laws of physics begin operating under extraordinary conditions. Gravity becomes intense. Magnetic fields become astonishing. Temperatures become remarkable. Neutron stars remind us that size and temperature do not always scale together. Sometimes the smallest objects become the most extreme. Black holes introduce another layer of complexity. Now things become truly strange. As matter falls toward a black hole, it often forms an accretion disk. This disk consists of gas spiraling inward at tremendous speeds. Friction and gravitational effects heat the material enormously. Temperatures within accretion disks can reach millions of degrees, sometimes far higher. The gas becomes so energetic that it emits powerful X-rays. Entire regions around black holes can outshine galaxies. The black hole itself remains invisible. The surrounding material performs all the dramatic work. This creates one of astronomy's favourite paradoxes. Some of the brightest environments in the universe exist around the darkest objects in the universe. If WR102 represents a stellar furnace, accretion disks around black holes resemble cosmic particle accelerators operating on scales beyond human comprehension. The comparison highlights an important distinction. WR102 remains one of the hottest stars. Black hole environments belong to a different category entirely. Then we encounter something even more surprising: galaxy clusters. These enormous structures contain hundreds or even thousands of galaxies. Between those galaxies exists gas, lots of it. At first glance, you might expect this gas to be cold because space itself feels cold. Reality disagrees. Much of the gas trapped within galaxy clusters reaches temperatures of tens of millions of degrees. The particles move at extraordinary speeds. Collisions generate tremendous heat. Entire regions spanning millions of light years become filled with superheated plasma. The scale is difficult to appreciate. WR102 may dominate its local environment. Galaxy clusters operate across distances so vast that individual stars become tiny details. Yet the temperatures remain extraordinary. Again, the universe finds new ways to surprise us. Even more astonishing are certain events involving neutron-star collisions. When two neutron stars merge, conditions become almost unimaginably extreme. Temperatures may reach hundreds of billions of degrees. Heavy elements such as gold and platinum can form. Gravitational waves ripple through space. Enormous amounts of energy are released. For a brief moment, nature creates conditions rivaling some of the most extreme environments since the beginning of the cosmos itself. Speaking of beginnings, we eventually arrive at the ultimate comparison: the early universe. Nothing else truly competes. Immediately after the Big Bang, temperatures exceeded anything we observe today. Not millions of degrees, not billions, far beyond that. The young universe was so hot that ordinary matter could not exist. Atoms could not form, nuclei could not survive. Particles behaved in ways fundamentally different from anything we experience today. As expansion occurred, temperatures gradually fell. The universe cooled, matter formed, stars eventually appeared, galaxies eventually emerged. Everything familiar developed from that cooling process. Compared with those earliest moments, even WR102 appears modest. That statement sounds almost unfair. After all, WR102 is among the hottest stars known. Yet the Big Bang established a standard that few cosmic phenomena can approach. So where does this leave our original question? Is WR102 truly the hottest star in the universe? The honest answer is that nobody can say with complete certainty. Astronomy is constantly evolving. New observations arrive. New stars are discovered. Better instruments reveal previously hidden details. There may be hotter stars waiting to be identified. There may be unusual objects in distant galaxies we have not yet measured accurately. The universe remains vast enough to surprise us. However, based on current observations, WR102 remains one of the strongest candidates for the title. Very few known stars possess comparable surface temperatures. Very few stars occupy such extreme territory. In practical terms, WR102 belongs among the hottest stellar objects humanity has ever observed. That alone is an extraordinary achievement. Imagine surveying hundreds of billions of stars in a galaxy and finding one that stands near the upper limits of known stellar temperature. WR102 occupies precisely that position. It represents an extreme outcome of stellar evolution, a star stripped of much of its outer material, a star exposing hotter internal layers, a star nearing the end of a remarkable life, a star pushing physical conditions to extraordinary levels. Perhaps the most interesting lesson from this comparison is not that WR102 loses certain temperature contests. Rather, it reveals how creative the universe can be. There is no single path to extremity. Stars become hot through fusion. Supernovae become hot through collapse and explosion. Accretion disks become hot through gravity. Neutron star mergers become hot through collision. The early universe became hot through its very origin. Different mechanisms, different environments, different scales, all producing extraordinary conditions. WR102 earns its place among these giants not because it is hotter than everything else that has ever existed, but because it represents one of the most extreme stars nature has produced. A stellar furnace operating near the limits of known stellar physics. A glimpse of what happens when mass, temperature, radiation and time combine in exactly the right way. After comparing WR102 with exploding stars, black holes, neutron stars, galaxy clusters, and even the early universe itself, one question remains. What does a star like this ultimately teach us about the cosmos, and about our own place within a universe capable of creating objects so vast, so powerful, and so astonishingly different from anything we experience on Earth? After spending so much time with WR102, it is tempting to think of it as an exception, a cosmic oddity, a strange object sitting far away in the Milky Way, living a life so extreme that it has little connection to our own. In one sense, that is true. Most of us will never personally encounter a star with a surface temperature approaching 200,000 degrees Celsius. Most of us will never witness a Wolf-Rayet star shedding vast quantities of material into space. Most of us will never stand beneath a sky dominated by an object like WR102, and yet in another sense this remarkable star is deeply connected to us. Perhaps more connected than it first appears, because the story of WR102 is not merely the story of one unusually hot star, it is also the story of time, the story of change, the story of how the universe transforms itself, and ultimately, it is part of the story that led to us. Throughout this journey, we've repeatedly encountered one surprising idea. Nothing in the universe remains exactly the same forever. Stars change, planets change, galaxies change, even the universe itself changes. The night sky can sometimes create the illusion of permanence. Constellations appear fixed, stars seem eternal, everything feels stable. Yet astronomy tells a very different story. The cosmos is constantly evolving. The changes often happen slowly, so slowly that human lives are too short to notice them directly, but they happen nonetheless. DSRW 102 reminds us of that reality. Right now, as you listen, the star is changing. Material continues flowing away through stellar winds. Fusion continues deep within the core. The internal structure continues evolving. The future continues approaching. Nothing has stopped. Nothing has paused. The star is participating in a process that began millions of years ago and will continue until its final collapse. In many ways, astronomy is the study of time made visible. When geologists study Earth, they examine rocks and landscapes. When historians study civilizations, they examine documents and artifacts. Astronomers study time itself through the lives of stars. Every star tells a story. Its temperature reveals part of that story. Its composition reveals another part. Its brightness reveals another. Its age reveals another. The challenge is learning how to read those clues. WR102 provides an especially dramatic example because it occupies such an unusual stage of stellar evolution. The star is effectively showing us what happens near the end of a massive stellar life. We're observing a chapter of cosmic history that relatively few stars ever experience, and by studying it, we learn something important about the universe itself, namely that creation and destruction are often the same process viewed from different perspectives. That idea appears repeatedly throughout astronomy. A star forms because gravity compresses a cloud of gas. The cloud disappears. A star appears. One thing ends. Another begins. Later, the star creates new elements through fusion. Hydrogen becomes helium. Helium becomes heavier elements. The original material is transformed. Something old disappears. Something new emerges. Eventually, the star dies. Its material returns to space. Future stars inherit that material. Future planets inherit that material. Again, an ending becomes a beginning. The pattern repeats everywhere. WR102 embodies that pattern beautifully. Its powerful winds are slowly dismantling the star. At first glance, that sounds destructive, and it is. The star is losing mass. The star is changing. The star is moving toward its final stages. Yet those same winds distribute valuable material into the galaxy. Elements forged through fusion spread outward. Future generations of stars may incorporate them. Future planets may incorporate them. The process appears destructive from one perspective, creative from another. Both views are correct. The universe rarely divides itself neatly into simple categories. Another lesson WR102 teaches involves scale. Human beings naturally think in human-sized terms. We measure distances in kilometers, lifetimes in years, temperatures in ways that relate to everyday experience. Astronomy constantly challenges those instincts. WR102 exists thousands of light years away. Its light takes millennia to reach Earth. Its temperatures exceed anything we encounter naturally. Its lifespan unfolds across millions of years. Everything about the star operates on scales far beyond ordinary human experience. And yet, remarkably, we can still understand it. Not perfectly, not completely, but meaningfully. That achievement is one of the great successes of science. Human beings evolved on a small rocky planet. We never evolved to understand stars. We never evolved to understand galaxies. We never evolved to understand black holes. Yet curiosity allowed us to investigate them anyway, piece by piece, observation by observation, question by question. Eventually we learned enough to reconstruct stories occurring thousands of light years away. The fact that you can sit comfortably in bed and think about a star like WR102 is extraordinary. Not because the star is extraordinary, though it certainly is, but because the human mind can reach that far. A species that once wondered what the lights in the sky might be now measures their temperatures, determines their compositions, predicts their futures. There is something genuinely remarkable about that. WR102 also teaches us humility. The universe does not organize itself around human preferences. Stars are not designed for our comfort. Galaxies are not designed for our convenience. Nature operates according to physical laws. Those laws produce objects of incredible beauty. They also produce environments completely hostile to life. WR102 is one such environment. Its temperatures would destroy anything familiar. Its radiation would overwhelm ordinary biology. Its stellar winds would devastate nearby worlds, and yet none of that makes the star bad. It simply makes it different. The universe contains extraordinary variety. Some places nurture life, some places forge elements, Some places create stars, some places destroy them. R102 happens to occupy a particularly extreme corner of that spectrum. The star exists as a reminder that reality is often stranger than imagination. If someone invented WR102 in a science fiction story, readers might accuse the author of exaggeration. A star with temperatures approaching 200,000 degrees Celsius, powerful enough to strip away its own outer layers, destined to end in a spectacular explosion. The description almost sounds excessive, yet nature arrived there first. Nature often does. One of the most fascinating aspects of astronomy is discovering that the real universe frequently exceeds our expectations. The cosmos is under no obligation to remain reasonable. Another idea worth considering involves perspective. Throughout history, people looked at stars and saw fixed points of light, beautiful, mysterious, distant. Modern astronomy changed that perspective dramatically. Today we understand stars as physical objects. They are born, they evolve, they age, they die. The lights in the sky became stories. WR102 represents one chapter within a much larger narrative, a narrative stretching back to the earlier stars and forward to future generations yet to form. When viewed from that perspective, the universe feels less like a collection of objects and more like a collection of processes. Everything changes, everything evolves, everything participates in larger cycles. Stars form from gas, stars create elements, stars return those elements to space, new stars emerge, the story continues. And somewhere within that story sits Earth, a small world orbiting an ordinary star, a planet assembled from materials forged inside earlier generations of stars, a planet where living creatures eventually evolved, creatures capable of wondering where those materials came from, creatures capable of studying stars like WR102, creatures capable of tracing their own origins back through billions of years of cosmic history. That realization may be the most remarkable part of all. When we study WR102, we are not merely looking outward, we are also looking backward. Backward through the history of matter, backward through the history of stars. Backward through the chain of events that eventually made our existence possible. The connection is indirect. The connection is ancient, but it is real. The atoms around us carry the evidence. Every element heavier than hydrogen tells part of the story. Every star contributes another chapter. WR102 is one of the more dramatic chapters. A star burning with extraordinary intensity. A star shedding its outer layers. A star racing toward a future explosion. A star helping shape the chemical evolution of the galaxy. A star reminding us that the universe is far more dynamic than it appears. And perhaps that brings us to a fitting place to end tonight's journey. Not with an explosion, not with a black hole, not with a record-breaking temperature. Instead with a simple observation. Somewhere in the Milky Way, thousands of light years from Earth, WR102 continues shining. Its light is crossing the galaxy at this very moment. Its winds continue flowing into space. Its future continues unfolding. The star does not know we exist. It does not know it has become one of the hottest stars ever studied. It does not know astronomers have spent decades trying to understand it. It simply follows the laws of physics, and yet, through observation and curiosity, we have managed to learn its story. A story about heat, a story about time, a story about starlight, a story about how the universe transforms itself, generation after generation, and perhaps, as you settle a little deeper into your pillow and allow the day to drift a little farther away, it is comforting to remember that the atoms making up this room, this planet, and even yourself have travelled through a universe far older and far larger than any of us can fully imagine. Long before cities existed, long before Earth existed, long before the sun existed, stars were already lighting the darkness, creating elements, changing the cosmos, preparing the ingredients for worlds that had not yet formed. The story continues tonight. It continued while you listened. It will continue long after this video ends. Somewhere out there, WR102 is still burning, still changing, still contributing its small part to a universe that never truly stands still.